Welcome to Hot Chips 25. The morning tutorial. Heterogeneous System Architecture. Overview and Implementation.
This is Phil Rogers from AMD. He is one of the people who really kicked off the HSA group, has a huge background in that area and in graphics. If he'll come up and kick off the tutorial, it would be great.
Thank you, Don. Good morning, everybody. It's good to see so many of you at 9 o'clock on a Sunday morning. I appreciate you coming out. We have 4 hours of what I hope you'll agree is very interesting material. We split the tutorial into 4 parts. I'm going to start off with an overview, introduce what HSA, the Heterogeneous System Architecture, comprises. I'll walk through the architecture at a fairly high level, show you the software stack, and conclude with a few example workloads that illustrate why we're building this architecture, the kinds of problems it solves. And I'll wrap up with a slide or two that illustrates the change in terms of programmability of the platform, making the platform easier for programmers. Following me will be Ben Sander, also from AMD. He's going to take you through HSAIL, which is the virtual ISA for parallel processing that's part of HSA. So it's a compiler target. People won't write programs in HSAIL. Compilers will generate HSAIL. But it's a very important part of defining the machine. He'll explain the structure of that ISA and give you examples on how it's used. After the break, Ben Gaster from Qualcomm will take you through the HSA Memory Model. This is obviously a very important part of any multi-threaded processing platform, how the threads interact in memory, what are the visibility rules, how do we synchronize. And then Ian Bratt from ARM will conclude the tutorial by explaining the HSA Queuing Model, which talks about how work is distributed across the system, how it is dispatched, how it completes, how it signals. And with that, we hope to give you a very good journey through the architecture. Previous presentations and other forums on HSA have been very much at a high level. This is the first time we're deep diving the architecture, so there should be a lot of new material for you. So I want to start by talking a little bit about the HSA Foundation. This is an architecture that's not developed by one company, but developed by a foundation, an industry-wide consortium of companies that recognize we need standards in this area. We need a platform standard in order for software to develop and flourish and take advantage of the SoCs that so many of the companies are already building. It's a new platform for heterogeneous systems. The foundation was founded in June of last year. Kicked off with 5 founder members. You'll see in the next slide, we have many more companies joining us now. There's a website there where you can find a lot of information, including specifications. The main activity going on in the foundation right now is development of the specifications that define HSA. One of those specifications, the PRM, which is the Programmer's Reference Manual, which is what defines HSAIL, is already available on the website. It has been published at a 0.95 revision. Other specifications are under active development in our working groups. These include system architecture, the HSA software runtime, and the HSA development tools. So here's the membership of the HSA Foundation. as you can see, there's a lot of companies here. And if you look across the founders, these are companies that put into the market much more than 1 billion processors per year. You see a number of companies here who have very much a focus on low power. And as you'll see as I describe the architecture, one of the key tenets of HSA is enabling our SoCs, enabling our platforms to process parallel workloads at much lower power than happens today. If you look across the breadth of companies at the different levels of membership in the foundation, you can see that we have companies who are OEMs, companies that make SoCs, companies that create IP, companies that do operating systems, middleware, tools. It's a very comprehensive foundation. This is an open foundation. Any of you are from companies or institutions who are not currently members of the HSA Foundation, we invite you today to join. If you go to the website, it's very easy to work out what level of membership is right for you and join in this very interesting work. You'll notice we have a number of academic members in the foundation. The academic sign-up is relatively recent. We have extremely reasonable terms for academic members to join the foundation. The annual fees are very low, and they're waived for publishing 1 paper per year in the area of heterogeneous processing. So why are we doing this? SoCs, system on a chip, have proliferated all across, I say all across most parts of the computing ecosystem today. They're in smartphones, they're in tablets, they're in notebooks, they're in PCs. They will soon be in servers as well. SoCs have arrived, and they're a tremendous advance over previous platforms. Not because they just consolidate and give an opportunity to reduce cost, but by combining the CPU, the GPU, multiple other accelerators, and high bandwidth memory controllers on a single piece of silicon, they give us new opportunities to advance the capability, efficiency, and performance of our computers, of our processing units. So how do we make them better? And first and foremost on that is how do we make them easier to program? Once we make them easier to program, more of the workloads that should take advantage of GPU compute and other accelerators will run much better on these platforms, higher performance, lower power. So what HSA does is it takes the different processors and accelerators and combines them architecturally. SoCs originally were an aggregation on silicon. With HSA, we do an architectural integration across all of the processors. The early focus of our work at the HSA Foundation has been on the GPU compute accelerator. It was obvious low-hanging fruit. We had very powerful parallel machines in the SoC that were being used extensively for graphics, but only being used partially for compute. Solving that problem brings an awful lot of performance and power savings to the platforms, but in doing this, we define an architecture that will work for other accelerators on that SoC, and we'll bring those in next. As you're defining a computing platform, it's important to look across the history of how we got here. This audience, I think, will be very familiar with these 3 curves. We had a single core era of microprocessors for decades. Every year or every other year, as we got new silicon, a new silicon node, we'd get more transistors, and we could immediately drive up performance for existing programs. However, that era hit the power wall. It hit it for a number of reasons. We constrained the power of the socket in almost every form factor. We've done an awful lot of microarchitectural optimizations. And the reality today is the gains to still be had in single-threaded performance are relatively modest. And in a lot of platforms, with the power envelopes being compressed, single-core performance could actually go down. The multi-core era served us for a few years as we added more CPUs to each SoC. However, this has also hit a power wall, both in terms of scalability, availability of parallel software in the client world, and again, this trade-off of power versus performance. This is what's led us to the heterogeneous system era and the proliferation of the SoC. Many companies have realized it makes more sense to use the additional transistors we're getting today with a balance of scalar CPU processors and parallel processors for graphics and parallel computing. This is also driven by the change in workloads over the past 6 to 8 years. We see far more video, audio, graphics, text analytics, big data being processed by the processors from everything from the smartphone to the cloud. However, this era, the heterogeneous systems era that we're really in the infancy, is temporarily constrained by multiple things, but in particular by today's programming models and communications overhead. And as you'll see as I take you through the rest of the architecture, HSA is designed to completely eliminate these constraints and let us soar through the rest of this era. The other thing to notice is that in each era of microprocessor development, we've seen an evolution in the availability of software programming tools that has led to the mass adoption of each platform. And in each era, the progression is eerily similar. We start with a very hard-to-use programming model that can immediately get the full performance of the machine. And then over the years, abstractions appear that make the platform accessible to more and more programmers. We give up a little bit of performance for those abstractions, but the number of programmers, the number of applications, the number of workloads goes up by orders of magnitude at each step. So in the single core era, we went from assembly language to structured languages, object-oriented languages, managed languages. In the multi-core era, we went from trying to program threads directly, which, probably most of the people who can do more than 2 threads are sitting in this room. Then we got to directives like OpenMP and task parallel runtime, which take programmers from having to reason about threads, which is very hard, to reasoning about tasks, which is much easier. In the heterogeneous systems era, we're early in this. People started programming shaders directly, then they moved to proprietary languages. Now we have standard drivers and standard programming languages like OpenCL and direct compute. But going forward, what opens up this era is enabling the full natural languages that programmers already use. Languages like C++, Java, Python, R, the list goes on. So how do we do this? I should have first of all explained the asterisk on this slide, and the asterisk applies to the whole tutorial. All of the specifications are still under development at the Foundation, so everything is subject to change. But I'm going to go through here the high-level features of HSA and what they each contribute to the platform. First of all, unified addressing across all processors. I'll talk in terms of GPU compute here, but a lot of these premises would apply to DSPs, to DMA engines, to codecs, security processors, all of the other accelerators that can come into this architecture. The first problem to solve is the addressing. Today on GPUs in almost all platforms, the GPU operates in a different virtual address space than the CPU. It has different page tables, and very often it's mapping completely different memory. We're unifying the addressing across all processors and having the accelerators operate by default into a common pool of coherent memory. In terms of unified addressing, this is extremely enabling. You can allocate memory on the CPU, pass that pointer to the GPU, and not only can that GPU now operate on that memory in place, if there's a complex data structure there, it can walk the data structure and find the parallel array it's going to operate on. Whereas in today's model, we have to pull that array out and index it. Operating into pageable system memory gives you 2 immediate benefits. First of all, the operating system and the driver did not have to page lock each page in place before the GPU can start on it. But secondly, it means that the GPU can now access all of physical memory and actually all of a processor's virtual address space. The double allocations and communications overhead that we have today will evaporate. Full memory coherency is extremely important in order to enable the full extent of high-level programming languages to run directly on the hardware. Today, most GPUs operate a protocol known as I/O coherency, meaning the GPUs can snoop the CPU caches, but not the other way around. With HSA, we have full memory coherency, which means that when the GPU is done writing data, the CPU can rely on finding that updated write wherever it is in the memory system. User mode dispatch. One of the common problems cited today in using the GPU for compute is the long latency between when a job is requested by the CPU to when it starts executing on the GPU. With user mode dispatch, we allow applications to put work directly into a GPU queue. If you think about how a task parallel runtime like threading building blocks or Grand Central Dispatch or Silk works, we're already used to the idea of CPU threads putting work in queues. Now the queues can be spread across a heterogeneous machine. An architected queuing language for the GPU, for compute. Today, each of the GPUs on the market execute from a dispatch packet that is proprietary to that machine, to that vendor. For compute, there really is no reason to have those differences. You basically want a pointer to the executable, a pointer to the data, a pointer to a structure that defines the layout of that data, and let the hardware go. So HSA includes an architected queuing language so that an application can put work in a queue, and whichever vendor is running that HSA platform can execute it. High-level language support for the GPU compute processor. In order to run full C++ or full Java, the GPU shader, the parallel processor within the GPU has to be upgraded with operations like being able to follow a function pointer to do a virtual method, throw an exception, and so forth. And finally, preemption and context switching. As we're looking to make the GPU compute processing pervasive, it's very important that the OS has the ability to provide a quality of service and time slice the machine. HSA is an open platform. That's what the HSA Foundation is all about. We publish the specifications so that software knows how the platform works and hardware can be built in a compliant manner. It's delivered via royalty-free specifications, very important in order to enable companies to work together, generate a specification, and know that they can safely implement it and ship it. It's ISA agnostic for both the CPU and the GPU. Again, extremely important in order to address this wide range of platforms from smartphones to supercomputers. And as you saw from the previous slides, we have membership in the HSA Foundation from all companies in the compute hierarchy, hardware companies, both IP and SoC, operating systems, tools, middleware. This is how you build an ecosystem. So the HSA Intermediate Layer, or HSAIL, is the virtual ISA for parallel programs in HSA. I won't spend a long time on HSAIL. This is the area that Ben Sander will do the deep dive when I'm done with the overview. But it's important to understand at a high level what this means. This means when a compiler compiles to HSA, it will generate HSAIL. And HSAIL was developed to be explicitly parallel. It's designed for high-efficiency data parallel computing. But it's not done in a form that favors one particular type of implementation architecture, microarchitecture. We defined it in SIMT form, single instruction, multiple thread. Ben will go through what exactly we mean by that and how it can apply to a wide range of different hardware architectures. We get a lot of questions about how HSAIL relates to SPIR, the new format recently announced by Kronos for OpenCL. And the answer is HSAIL is at a lower level than OpenCL SPIR. It's designed to solve a different problem. In particular, SPIR from OpenCL was specified and generated to provide immediate portability for OpenCL and a way of allowing the application developers to hide their code and not have to ship source code in order to ship an OpenCL program. We designed HSAIL around a particular goal to keep it very low level, allow the optimizations to go to the high-level compiler, and on platforms where there is a just-in-time compiler, keep that JIT time small. And again, Ben will go more into this. When you're defining a multi-threaded platform, it's extremely important that you have a rigorous and well-defined memory model so that programmers understand how their threads interact in memory and how to synchronize them, and hardware developers know how to build a compliant platform and can be sure that their platform is correct. So Ben Gaster will give you a deep dive through the details of the HSA memory model. The thing I wanted to point out is, as we were developing this memory model, the key thing to us was that it needed to support all of the high-level languages, and many of the high-level languages already define their own memory models. So as we went through the design process, we ensured that the HSA memory model is compatible with the C++11 memory model, the Java model, the OpenCL 2.0 memory model, and the .NET memory model. We're all about enabling those high-level languages to run and to run in the way they're already defined. We're building a platform to match the software, not building a platform and asking the software to change to match us. As Ben will explain, this is a relaxed consistency memory model, and he'll explain not only what that means, but the particular aspects of the one we've implemented here. And it's synchronized by load, acquire, store, release semantics, and barriers within workgroups. The HSA queuing model. This is the piece that the third deep dive will cover. This will describe how and why we do user mode queuing for low latency dispatch of compute jobs. The application is able to dispatch directly. This means there's no need for a driver and an operating system between the dispatch and your execution on hardware. As I mentioned, it's architected, a single dispatch packet format for all hardware vendors, single target for software to use. It allows for dispatch to the queue from any input or from any processor. So this isn't just to enable the CPU to offload work to the GPU. It's also for the GPU to re-enqueue work to itself. And the re-enqueue of work, self-enqueue by the GPU, is an extremely powerful paradigm that, again, opens up the platform to new algorithms. So I want to talk now a little bit about the HSA software and what the software stack looks like on this platform and what it looks like to programmers writing applications and libraries. So first of all, I want to compare how the HSA software stack looks when put next to today's driver-based stack for GPU compute. On the left side, you see the driver stack. You'll notice the broad vertical arrows. These represent the high bandwidth, command, and data traffic. I haven't shown any control paths on here. I'm focusing on where the performance and the overhead is. On the driver stack, for an application to reach the hardware, it has to go through multiple layers of software. Typically, it will call a runtime, which calls a user mode driver, which calls the OS, which calls back to the user mode driver. Ultimately, we fill up a command packet, and we call the OS, which parks it. And then at some time later, it calls the kernel mode driver to format it, and then it queues it. So you can understand there's a lot of delays and unpredictability in that path. If you look on the right side with the HSA stack, the first thing you should notice is on the left side of that, there's an arrow from the application straight to the hardware. An application, a user mode application, can put packets directly in a hardware queue. Now, of course, we don't expect all applications or even a lot of applications to do that, but we do expect a lot of applications to call libraries, optimized libraries, domain libraries, math libraries that will do exactly that. Other applications may cause task queuing libraries, which will also be layered directly on the queue. You notice there's a JIT compiler hanging off in space there. That's because it gets invoked periodically for new code. It's not invoked in every high bandwidth path. And also on some platforms, particularly closed platforms, the finalizer may be run compile time. So the JIT is there more for open platforms. You'll notice we still have a runtime and a kernel mode driver, but we show them off to the side. They're off to the side because they're used occasionally. They're used at initialization, teardown, memory allocation, fault handling, and synchronization. They're not used in the high bandwidth paths, hence we achieve very low overhead dispatch. It's important to talk about how OpenCL relates to HSA. HSA is an optimized platform that's extremely good at running OpenCL programs. And as OpenCL and HSA evolve, we see a lot of commonality. If you take an existing OpenCL program and run it on an HSA platform, you very likely immediately see a performance improvement and an efficiency increase. We avoid all of the wasteful copies and stay in the original memory. The dispatch becomes immediately lower latency, and you get an improved memory model. I say in most cases you'll see an improvement because obviously today a lot of programs have programmed around the current model, meaning they do very large batch dispatch. Over time, the dispatch size can come down and you see a lot more improvement. On any new platform, it's important to provide libraries to immediately allow programmers to be productive. With HSA, the parallel primitives library is called Bolt. It allows programmers to easily use the parallel features of the machine and also the heterogeneous features of the machine. So in addition to common routines such as scan, sort, reduce, transform, we also supply heterogeneous platform pipelines to enable you to run different stages of your algorithm on different processors. An early preview of Bolt is already available online. There's a link there in the slide deck. And this version of Bolt supports both OpenCL and C++ AMP as its first programming models. HSA is being designed to support open source. And in particular, we will have an open source execution stack available for Linux. I've listed the different software components here that will be open sourced. And in the middle column, I make the distinction on whether these modules are common, meaning that they're applicable across multi-vendor, or whether they're specific to an IHV, an independent hardware vendor. There's a lot of reasons for going open source here. First of it is to prevent fragmentation unnecessarily of the platform. Having common software modules for multiple parts of the stack mean that the programmers, the application programmers, get a uniform experience through those software layers. For the IHV-specific parts, having an open source kernel driver, of course, means it can go upstream to kernel.org and then feed its way down through the distributions. Finally, it enables university research. Heterogeneous platforms, heterogeneous programming, optimization, libraries, new algorithms, an extremely rich area for research. We're opening it up. A lot of work that's gone on in GPU compute and heterogeneous computing has focused initially on native languages. We think there's a very good opportunity, actually a vast opportunity, for heterogeneous platforms in the cloud. And in big data and cloud and server processing in general, the predominant language is Java. So what do we do about accelerating Java on HSA? Well, it turns out that we've already made a good start here with an open source library called Apirapi. This is a Java library that allows a Java developer to link in a Java library, write parallel code in Java, and then at runtime, it converts the Java bytecode to OpenCL and can accelerate on an OpenCL compliant GPU. Also, if there isn't such a GPU in the system, it will accelerate the workload across a thread pool on the CPU. So Apirapi has been enabling some early parallel development on Java. But as we looked at the roadmap that we would like for Apirapi, how would we evolve it over time and optimize it, layer it directly on HSAIL, add in some optimizations? We realized ultimately that the parallel acceleration belongs in the Java virtual machine, and that's where it would ideally reside. Project Sumatra has been started to achieve exactly that. So Sumatra is an open source OpenJDK project. It's sponsored by AMD and Oracle, and it's targeted at the Java 9 release, which is scheduled for 2015. It builds off of the Lambda function, which was added to the Java language for Java 8. In Java 8, it's targeted at multi-core CPU acceleration. With Project Sumatra, we extend that across to the heterogeneous platform, and you get HSA acceleration. You can see there's a number of web links there where you can get a lot more information, real-time information on the progress of Project Sumatra. So now I want to go through a few workload examples. The first one, HAR face detection, is taken from photo search or video search. And while the example is in terms of faces, the algorithm and the principles discussed here apply much more broadly than that to object recognition, gesture recognition and extraction, and so forth. The way the HAR algorithm works is it uses search squares to search across a frame of video. For a particular size search square, 21 by 21 on HD video, we're talking about 2 million search squares a frame. Then you progressively shrink the frame in order to look for different size faces, and you're at about 4 million search squares. The way the algorithm works is it looks sequentially for different features in each search square. And if it doesn't find them, it rejects the frame. So this is an early out algorithm. In this particular instance of the algorithm, there are 22 stages. At each stage, if it rejects, we have no face. If we get through all of them, we believe we found what we're looking for. So if you think about that in terms of calculations, we're up to 47 billion calculations per frame, and at 60 frames per second, 2.8 trillion calculations per second. So obviously there's a lot of parallel processing here. You'd think this would be a great fit to just run the whole thing on the GPU. However, early out algorithms don't do well on SIMD engines. Right? At each stage, we have threads exiting, which means as we go through those cascade stages, the SIMD packing and the GPU efficiency goes down. And GPUs and SIMD engines in general don't do well when their packing is below 50%. So what to do? Especially given that in an average photo or video frame, the vast majority of the search squares are going to exit in 5 cascade stages or less. Here's what it looks like in terms of time. On the left, you see the first stage. And time, this is a plot of time, so lower is better. And the GPU finishes in about 1/6 the time of the CPU. Far, far more efficient. Second, third, and fourth cascade stage, the CPU and GPU are about equivalent. It's a wash. For every stage beyond that, the CPU wins hands down. The answer is you run the stages on the GPU that it's good at, and you run the stages it's not good at on the CPU. Let the CPU run where it's best. Move the compute, not the data. This is an optimization that you can do on HSA because everything is running in the same memory with the same addresses, fully coherent. The processing can shift at any time with efficiency. And what we see here is if we run the first 3 stages on the GPU, finish the frame on the CPU, and start the GPU on the next one, we get the best outcome, which is 2.5 times performance speed up, or if we're running at a constant workload, we run it at 40% of the power. And more, the calculation that matters is the one on the right, reducing the number of joules per operation, or microjoules or picojoules, however you want to calibrate. The next workload is interesting because it's not related to graphics or video or audio or any of the often cited examples in GPU compute. This one is about text analytics, big data, searching enormous archives of documents for themes, memes, phrases, events. Suffix arrays, fundamental data structure, used very pervasively for searching text. Quickly locate every occurrence of a substring S in a text T, which really means words in a document D. Suffix arrays are used in a wide variety of applications, not just text index search, but data compression, bioinformatics. There's a much longer list here. This one illustrates a different place where a heterogeneous architecture like HSA excels. And what I mean here is instead of dividing a single algorithm by different data and execution patterns, here we're taking a pipeline that has multiple different types of processing in it and recognizing that some work well on one processor and others work well on a different one. And in this case, suffix array construction is a series of sort, rank, construct the array, sort, and sort again. And the GPU is very good at the sorts, the CPU is excellent at the rank and at the array construction. When we structure the pipeline that way, move the compute to where it belongs, leave the data where it is, we can get over a 5 times performance increase or run in 1/5 of the power. Rigid body physics is an interesting example. Physics simulation gets used in a lot of places. I've dealt with it extensively in games. It's also used in authoring tools, in engineering packages, industrial applications, medical, robotics, and many more. In games, it's interesting in that the physics in games often splits into 2 parts, what we call gameplay physics and eye candy. The gameplay physics calculates the interactions between the players, the non-playing characters, the buildings, the roads, the projectiles, and then calculates what happens in the next frame. The eye candy physics is all about special effects, smoke, flames, explosions that don't impact bodies, getting the ocean or running water to look correctly, or cloth waving in a breeze. The difference between the gameplay and the eye candy is the gameplay physics has to happen quickly and be fed back to the CPU in time to calculate the next frame. The eye candy physics can be pipelined along with the picture creation down the graphics pipeline and doesn't feed back to the CPU. On today's GPUs, and in fact on most SoCs that run games, the eye candy physics goes to the GPU. The gameplay physics has to stay on the CPU because of that tight interaction with the CPU. So if you look at the challenges versus benefits, we see that HSA changes the platform to the point that gameplay physics can now be accelerated. Some of the challenges previously were this tight interaction between the game engine and the physics engine, which can be solved with user mode dispatch, the shared memory, the coherency, and the quality of service that could enable the gameplay physics to have priority and actually get ahead of the graphics pipeline. The next barrier is the sheer size of the data sets in physics can be enormous. So allowing all of memory to be used for those data sets, and of course only the memory pages that are actually being touched, also opens the door here. And finally, the narrow phase algorithms that are part of the rigid body physics calculation can really only be accelerated on the GPU when the GPU has the ability to queue to itself. So I want to finish here by going back to talking about this ease of programming. In many ways, what HSA does that revolutionizes here is enabling these high-level programming languages, in other words, making it easy for the programmer to use the accelerators that are in the machine. So I wanted to look quickly at an example here that illustrates it. And the way we're looking here is using the measure of lines of code for code complexity. Now, all of us who are programmers know that lines of code are not a complete barometer for code complexity, but it's a good thing to look at first order. These colored columns here represent lines of code from left to right for different implementations of the same algorithm. And in this case, it's an image processing algorithm called the Hessian kernel. And on the left side, you see it programmed for a serial CPU, then for a task parallel runtime, then for a task parallel runtime with intrinsics, because I think some of us know that to get the full performance out of a CPU, we actually sometimes have to go to assembly code. Then to OpenCL in its first incantation, OpenCL 1.0. And then, as you see to the right, we start coming down in code complexity. Well, why did anybody go to this level of complexity to begin with? Well, the answer, of course, is performance. So the gray bars show the performance that was achieved at each stage of this exercise. When you go from straight serial programming to a task parallel runtime to use all of the cores in the machine, you can get about a 3x speed up on a 4-core machine for a code complexity increase of about 30%. You go with the intrinsics, you can get another 4x, but you double your code complexity. With OpenCL, you can double again, but not only do you add more lines of code, but it's different kinds of code, and it requires a different kind of expert to write it. So the point is, as we were going up towards the middle here, we could get the performance, but the number of programmers who would do it was diminishing at each stage. As we come down the other side, you'll notice that we're diminishing the code complexity, but we're really not giving up very much performance. So with OpenCL 1.2 and C++ kernel language, the lines of code to use that OpenCL have come down dramatically. The performance didn't. C++ AMP, the single source programming for parallel machines as part of Visual Studio, it came down again. You go to HSA and use the Bolt library for the Hessian kernel, and you're at a code complexity level very similar to the serial CPU. So this is the future that HSA is going to bring to you. It's architecting the heterogeneous processing on the SoC. It's making it so that programming that whole platform becomes much easier, which brings us accelerated software that runs across multiple hardware vendors, and not just across multiple hardware vendors, but this architecture will scale from the smartphone through the PC to cloud servers and supercomputers. While GPU acceleration for compute is the initial target, we're defining an architecture that will work across all of the accelerators in the SoC. This will result in the heterogeneous software ecosystem expanding much faster than we see today and brings lower power, more capable devices at every point in the infrastructure. Thank you. So Ben Sanders is going to take us through HSAIL now, and at the end of his talk, we'll both be available for questions.
All right, thank you. So good morning. Get my slides up here. Perfect. Give me just a minute. What's that? Is this where I'm supposed to stall? So let me just kind of start. The first ones don't have a lot of content on it. So good morning, everybody. As Phil mentioned, I'm going to talk about HSAIL, which is our portable intermediate representation. It's really a compiler IR, and it does have some parallel features. So if I can get my first slide up here, which has some great pictures on it, I'll get us started. Perfect. Okay, so I wanted to start with a bit of motivation for how HSAIL fits into the overall story of HSA. And where I thought I'd start was just looking at the state of GPU computing in general. It's pretty well established at this point that GPUs are very fast and very power efficient. They're a very, very good technology for doing computing. Intuitively, that makes sense. You know, if you look at how GPUs are put together as compared to CPUs, the GPUs strip away a lot of the pipelining. The GPUs don't really focus on out-of-order execution or big register files. They're really just focused on the ALUs and the compute without a lot of the latency hiding or latency optimization techniques that go into CPUs. So that's the intuition. And if you look at the results, for example, the top 500 list now, which shows the fastest supercomputers in the world, that's now dominated by GPU computing. And the same is true of the green 500 list, which shows the most energy efficient computing devices in the world. That also uses heterogeneous or GPU-based computing. So the technology is very, very good for compute density. But the challenge that we see today is that these devices are very, very hard to program. And there's really two reasons for that I wanted to explore here. The first one is this notion of separate address spaces. So if you think about how a typical system is put together, you have a CPU device which has its own memory, and that's kind of shown in the picture here. And it's typically, the accelerator with the GPUs on it is across a bus, like across a PCI Express bus. So in order to benefit from that acceleration, you have to copy all your data over to the accelerator and then run the algorithm there and then copy the data back over to the CPU. And the copies are inefficient. They also do some damage to the programming model because it's not as intuitive to have these copies in the middle. The real place where that damage occurs is in the use of pointers. So because there's a separate address space, if I have a pointer on the CPU and I copy it over to the GPU, it doesn't point into anything relevant. It doesn't point into the GPU address space anymore. So if you have data structures that use pointers, which is pretty much every program in the world, you either can't take advantage of this GPU acceleration, or you have to repack your data and kind of re-index the pointers into this new address space, which is an extremely cumbersome process. So for this challenge, we kind of already have the solution, which is these HSA computing devices. You know, if you buy a personal computer today, if you buy a cell phone today, if you buy a tablet today, we've already taken the CPU and the GPU and put them on the same piece of silicon, and they share the same memory. So the technology is almost already here. What HSA does is kind of raise the bar a little bit for how those things interact when they're on that same chip, and it provides standards that all the vendors will follow. So if we think about what do I mean by raising the bar, we're talking about a single address space, so you can pass these pointers back and forth. It's coherent, as Phil mentioned, so you can do very fine-grained communication between the CPU and the GPU. It's virtual addressing. So no longer do you have a small amount of memory that your accelerator can access. It's actually virtual, pageable. It can get to gigabytes or terabytes of memory, and that can be paged as well. Fast access from all the components. So both the CPU and the GPU can get at this memory very, very quickly, and you can share pointers, which unlocks this barrier that I mentioned earlier. The second challenge we see with programming these things is that they typically require a new, different programming language. So OpenCL is a good example. So there's a very small number of people in the world that understand how to program in OpenCL. It's a fairly complex runtime API. Phil showed the lines of code in his last slide. So it really does take a fairly special person in order to program in OpenCL. And what we'd really like to do is not require you to learn something new. We want to bring these benefits of GPU computing to the programming languages that the programmers are already using. The other challenge with OpenCL is that the code for the GPU is compiled separately than the code from the CPU. So you tend to end up with your host code over here, and then you've got a special section that's for the GPU. And obviously that's somewhat undesirable. One of the things we see is people that have a program that runs on a CPU, when they develop the OpenCL version, it's a completely separate code path. So now you have 2 pieces of code to maintain. That's undesirable. You'd really like to get back down to 1. Okay, so with our goal of bringing GPU computing to these existing languages, this is where HSAIL, which is the theme for the rest of my talk, this is where that kind of fits into the picture. And what we want to do is get to, first of all, a single source, fully supported by the compiler. So Java is a great example. What I really want to do is I'm in Java, and all I do is mark my parallel region that I think can take advantage of GPU computing. And the compiler and the tools take care of parallelizing that loop and making it run on my best available accelerator. HSAIL is a critical part of that solution because it's a portable compiler IR. What I mean by portable is it runs across all the vendors that are part of the HSA Foundation. So if I kind of pause here and kind of survey the crowd here, how many of you guys would consider yourselves to be CPU hardware designers? So that's perfect. So the way that CPU tends to work, about every 2 years or so, we evolve the instruction set for the CPUs. And it's almost always backwards compatible, so all your code continues to run. And we add in a handful of new multimedia instructions. GPUs are completely different. GPU ISA, we basically change that as often as we possibly can. And it's done, and there's 10 or so different vendors, all evolving the ISA. None of them are compatible with each other. There's nothing like ARM or x86, which is supported by multiple vendors. There's lots of different vendors. We don't maintain any kind of backwards compatibility at all because it's all written by drivers. So if you think about the challenge this presents when we're trying to change programming models, if we go to a compiler vendor and we say we want you to generate 10 different instruction sets, and by the way, we're going to change it in a year, we're going to want 10 new ones, that's a tough sell. If we go to application developers and we say we want you to generate a fat binary that has 10 different ISAs in it, and it'll be obsolete in a year, that's a very tough sell. And that's really the problem that HSAIL solves. Because we've gotten some commonality among the GPU vendors, we've got a portable layer which can reach all these different targets. This gives a stable target for compiler vendors to target, which gets to all the different GPUs they want. And it also gives application developers a way to ship their code in a way that's forward compatible. So that's my introduction. Let me give a little bit more detail. What is HSAIL? So HSAIL is the intermediate language. So by intermediate language, we mean it's intermediate to the compiler. So you can write code in HSAIL. It basically looks like an assembly language, and we'll go into some examples later on. Typically, it's going to be generated by a high-level compiler, however. So for when we say parallel, I talked about Java and the fact that what we want to do is have the programmer just marks a parallel region of code. Typically, the HSAIL would only be generated for that parallel region of code. The rest of the program would be compiled for the host instruction set. HSAIL also has some features for parallel computing, so I'll get into the execution model and how that works later on in the talk. It's a low-level intermediate representation, so it's very, very close to the instruction level. So what that means is most of the optimizations are done before you get to HSAIL. We have this tool called the finalizer. So we've got all these different vendors that I just talked about, all with their own instruction sets. The finalizer is the tool that takes the HSAIL and generates the ISA for all the different possible targets. Finalizer can be run at runtime. So what that means is you'd get a binary that contains HSAIL, and when you run the application, that's when we run the finalizer to generate the ISA. You can also do it at install time. So if you imagine a cell phone, for example, when you download your program, we could finalize for that target instruction because it's not going to go to any other platform. Or you can do it at build time. So the developer who knows the characteristics of the system he's targeting, portability is not a concern. He can go all the way down to the ISA by running the finalizer at build time. So I wanted to show on the second part of this slide an example of a sample compilation stack using OpenCL that contains HSAIL. So if we start with the picture on the left here, this is the flow that a developer might go through. So starting with an OpenCL kernel that's written in the OpenCL kernel language, typically that goes through a front-end compiler like EDG or Clang, which takes that OpenCL kernel language, translates that into a symbol table. There's a high-level intermediate representation called SPIR that Phil mentioned. I also have a little bit more information on this later on in the talk. So you go through SPIR, then you would go through LLVM in this example. So LLVM would do some optimizations on that code, would generate HSAIL. In this model, the developer would ship a binary that contains that HSAIL code. Excuse me. And so we're right here in the middle of this picture now. So when we get to the user system, we have this binary contains HSAIL. The user runs the finalizer tool. Finalizer generates the hardware ISA, and that's what actually runs on the machine. I wanted to go through some of the key features of HSAIL. So I mentioned that it's parallel. We'll talk about the parallel execution model in a second. Essentially, one of the really nice things about HSAIL is that the programmer only writes a single thread of execution. And the execution model that surrounds that takes advantage of exposing and exploiting the parallelism on the system. We'll go through that in some detail in just a minute. Fundamentally, HSAIL supports shared virtual memory. So this is this notion of a CPU and a GPU being able to share pointers that's built into the characteristics of the language itself. HSAIL's portable across multiple vendors in the HSA Foundation. It's stable across multiple product generations. So we intend for this to be a binary distribution format. So it's important that those binaries continue to work across multiple product generations. Consistent numerical results. So we have standardized and agreed on IEEE 754 precision and accuracy requirements, so those are built into the specification. So if you run this program on different hardware, you have some guarantee that you'll get the same result. Fast, robust, and simple finalization step. So HSAIL, we've mentioned, is very close to the hardware, so there's not a lot of work to do in that final translation step, and that's really useful because it provides less opportunity for things to go wrong, basically. So we don't need to do monthly driver updates of this finalizer. It's intended to be a very stable tool. Good performance, because you are very close to the ISA. There's not a strong motivation to go write things in the native ISA for the machines. It's got enough features to support all of OpenCL and all of C++ AMP. And it also has features that are forward-looking as we look to newer languages like Java or C++ or other languages. Okay, so the agenda for the rest of the talk. So I've done the introduction. I'm going to talk about the parallel execution model. I'm going to give some details on the instruction set. I've got an example that's actually written in Java and generates HSAIL, and then I'll summarize the talk. Okay, so this is an introduction into the execution model. The basic idea here is that the programmer is going to supply what we call a kernel. And the kernel is going to be run on every work item. So I don't know, this they told me doesn't work. So you probably can't see it. So the programmer supplies this kernel which runs on every single work item. He also supplies a grid, which is this big rectangular object on the left-hand side of this screen here. The grid basically specifies the dimensions of the problem. So we have the kernel, and it's going to be run across all the different work items in this problem. There's a further subdivision that's possible. You can take this grid and divide it up into work groups, and there's some additional communication that's supported within the work group. So there's special memory. The work items that are part of a work group can communicate very effectively with each other. Let me go to the next slide, which has a more detailed example. So this is my dog, Peaches. What I wanted to do was talk about running a convolution filter on this to do edge detection. And what we're going to do is take this algorithm that's described in the middle, this part here in the middle. So this is a simple edge detection. So if you look at it, it's looking at the surrounding pixels. So there's a three-dimensional matrix there. And That'll help. Okay. Thank you. Okay, so let me use this to talk about this a little bit more effectively. So if you look at the matrix here, and you consider this is the center pixel. So we're going to look at the 8 pixels that are surrounding that one. And you can see if all the pixels are the same, we'll essentially end up with a 0 value. There won't be any change that's detected. But if we get a difference in the pixels, where some of these are a smaller value and some of these are bigger, then we'll start to see some differences in the pixel gradation. And that's how we'll detect the edges. The detailed math isn't really important. The thing that's important is that we're looking at the pixels that are neighboring an individual center pixel. What we want to do is run this mathematical calculation across every single every single pixel in the image. So it's a very, very parallel problem. And what I want to do is take this problem and kind of cast it in terms of the HSA terminology for a kernel execution, or the execution model. So this would be the kernel. So this would be written in HSAIL. This would target a single work item in the image. A work item in this case would map to a single pixel. And then the grid that we specify, which gives the range of the problem, because we're using an image, that would define the square, the coordinates of the image, the x and the y dimensions of the image. Okay. There's also this concept of work groups that I briefly mentioned before. So it's possible to collect the work items together into a work group. And within the work group, there's something called group memory, which can be used for very efficient communication between the work items. So in this case, recall that every single one of these work items is looking at the surrounding pixels in the x and the y dimension. We could theoretically use this group memory to facilitate that communication. So I might load the surrounding pixels into group memory, and then when I run my work item, I would have very high performance access to the neighboring pixels that I need in order to perform this calculation. So the key points here are that when the HSAIL, the piece of code that the programmer is providing, is really targeted at just a single work item. And that's beautiful because programmers are used to dealing with single threads. They're very comfortable programming in a single threaded manner. The parallelization specification and how that's provided is through the grid and through the work group that really specifies how I want to take that single thread and apply it across a bigger problem. So we have a very clean separation between what the programmer provides as far as the code that's executed and then how the parallelization is specified. Okay, I want to shift gears here a little bit and talk through some of the characteristics of the instruction set, in particular how HSAIL differs from other compiler intermediate representations, because there are a lot of them out there. HSAIL is similar to an assembly language for a RISC CPU, so it's a load store architecture. So if we look at this load instruction, this is a load instruction. It's from the global address space. I'll talk about segments in the next slide. It's an unsigned 64 type. The destination is typically first at HSAIL instructions. So D0 is the destination. The D6 plus 120 forms an address. So we're going to do a load from that address and put the result into D0. The add is another example instruction. So this is an add with an unsigned 64 type. The destination here is D1. So we're doing D1 equals D2 plus 24. So very, very similar to other intermediate languages or other assembly languages that you may have seen before. There's about 136 opcodes in HSAIL. So as compared to Java, Java has about 200 opcodes, so kind of similar. We support floating point, so single precision, double precision, and half floats or F16s are all natively supported by the instruction set. Integer operations as well, 32-bit and 64-bit. There's some packed operations, so you can do 8-bit packed or 16-bit packed, 32-bit packed. That can be useful for some operations like media applications, for example. There are branches that are supported in the instruction set, function calls. The final point here, there's platform atomic instructions. So I've listed the atomics here, which are basically logical operations and arithmetic operations. plus a CAS operation. But the key point is that they're platform level. What I mean by platform level is that the atomics operate on memory between both the CPU and the GPU. So these aren't just specific to the GPU device or the HSA component. They go across the entire platform. And that's really leveraging the fact that kind of the bar of entry for HSA are these SoCs where these things are already integrated together, and so they have shared memory. Now we're exposing this through the instruction set and allowing this really kind of tight communication. There is a text format of HSAIL, so the examples I'm showing here are in the text format. Text format is useful if you want to write HSAIL or if you want to look at example programs or disassemble it. There's also a binary form of HSAIL. So in the examples where we talk about people shipping programs with HSAIL, we anticipate that they would bundle the binary form. The binary form is a bit more efficient for translation by the finalizer. Okay, I wanted to spend a couple slides on segments. This is one of the things that's a little different from other intermediate languages, in particular the group memory that I've mentioned before. So HSAIL supports 7 segments of memory. They are global, read-only, group, SPIL, private ARG, and kern ARG. I'm going to go through those one by one over the next slide or two. Memory instructions for HSAIL can optionally specify one of these segments. If you don't specify a segment, you get something called flat memory, which I'll talk about on the next slide, but essentially it lets you get to any of the segments if you don't specify one explicitly. So here's a couple examples. So we've got just using the global segment, load from global space. This is a load from group segment, load from or store to the SPIL segment. So you can specify this as part of any of the instructions that you use. The global segment is the one that is visible to all the HSA systems, so including the host and including the host CPU and the GPU. So this is an efficient way to pass data back and forth between the CPU and the GPU. This pointer sharing that we're using could use the global segment. Group segment. So this is the memory that is specific to a work group. So every work group has its own group memory. The work items within that work group can read or write to the group memory. Typically, group memory has special hardware acceleration, so it's a very efficient way to communicate. A work item can write a piece of data into group memory, and another work item in that same group can pick it up and see that data. There are, HSAIL provides we call them sync operations to control the visibility. So if you do a write and you want somebody else to see it, you have to stick a sync operation in there to make sure that it's visible. This can be useful for expert programmers to take advantage of this high performance memory. It does complicate the code somewhat. You know, if you think about the convolution example, and we would load data from that original image of the dog into group memory. Then when we write our kernel, we'd have to synchronize, and then we'd have to pull the data out of that group memory. So you're basically kind of re-indexing the code. It can get somewhat complicated for longer pieces of code. The code gets a little bit harder to read if you use group memory, but it does provide peak performance and access to this high-speed memory. So we call it useful for expert programmers. The SPIL, private, and ARG segments, so I kind of lump these together because they're essentially different pieces of a stack. So if you think about a function call on a CPU, typically we use a stack to communicate the arguments. So those are pushed onto the stack, and the function can pop them off. So that's the ARG segment, the last one listed here. Local variables are also allocated on a CPU function stack, and there's usually some space for spilling registers. So HSAIL has those same concepts. The difference with HSAIL is that they're explicit in the intermediate language, and this can sometimes be useful for optimizations done in the finalizer. So for example, SPIL is a really good example here, where a clever finalizer may be able to take some of the spills and reallocate those to registers. Excuse me. So the fact that they're not just explicit stack references, but we actually identify the segment can help to facilitate that optimization. The other thing that's interesting to note about these segments is that they tend to be indexed differently than the other pieces of memory. The hardware will do different swizzles, we call them. But if you think about a naive way to organize the private SPIL and ARG would be for every work item to have a consecutive block of memory, and then we do the next work item, the next work item, the next work item. Because these instructions tend to execute at the same time, if each instruction acts as the first element in its argument storage, those accesses would actually be spread out in memory, which is not a very efficient way to access the memory. So these segments tend to be swizzled, meaning that the first 4 bytes of work item 0 is right next to the first 4 bytes of work item 1, next to 2, so that these access patterns that are common result in a very tight coalesced access to the memory. So that's another characteristic of these 3 segments. Okay, the kernarg segment, so this is a segment of memory that is used to pass arguments to the kernel. So typically, the way that this would work, the host would allocate a block of memory, and it would start to write the arguments for the kernel into that space. When we actually get into the kernel, it would reference the kernel argument in order to pick up those arguments. So again, going back to the dog example, some of the arguments that the kernel is going to need, it's going to need a pointer to the data that contains the input image. It might need a pointer to the output image. Those coefficients that were hard-coded there, you could imagine those being extra parameters. All of that information would be passed through this kernarg segment. HSAIL also supports a read-only segment. So this remains constant during the execution of the kernel. This can be useful. In particular, some of the hardware, some of the HSA hardware has read-only caches, and so it's very useful to know when you can use that hardware versus when you can't. If the data is read-only during the execution of the kernel, then we know that we can use that hardware. So I mentioned flat addressing earlier. Essentially, the way that this works, all of the segments that I just talked about are mapped into the virtual address space. So if you look at the whole address space, there's a carve out for group memory, there's a carve out for the private arg and SPIL section in the virtual space. And what that means is I can get from a virtual address, I can index into those segments, as opposed to having to explicitly identify it in the instruction. The examples I showed before, there was a load from group memory. So I had to know when I generated that instruction that it was going to go to group memory. Flat memory removes that restriction because I can get there from the virtual address. That turns out to be extremely useful when you're writing classes or functions that take pointers. You can imagine if I had to pass a pointer to a specific segment like group memory, I had to know it was group memory so that I could generate group memory instructions. If you have a function that takes a lot of pointers, you have to generate a lot of code because you need one version for group memory, one version for private memory, one version for global memory. You get lots of arguments, it kind of explodes. So flat memory is extremely useful for enabling these higher level programming languages and higher level constructs like pointers and classes. OpenCL 2.0 has also added a similar feature, which is called generic addressing, very, very similar concept to HSAIL's flat addressing. The way that you use that, I've got a simple example here, is you just don't pass a segment. So this one is an explicit reference to the kernarg segment. The next example doesn't specify a segment. That's going to go to flat. Okay, register. So this is a key feature of HSAIL that's different than some other intermediate languages that are on the market. Let me just start with kind of the organization of the register file, and then we'll talk about the trade-off here. So HSAIL has 4 classes of registers. We have control registers, which are used for comparison instructions. So you do a comparison, that goes into a control register, and then you do a branch that looks at the control register. We have 3 classes of data registers, so those are S, D, and Q. S are 32-bit registers, so those can hold a floating point value or a 32-bit integer. We've got D values, which are 64-bit, so those are a double precision floating point, or you can put a 64-bit integer in there. And then we've got these packed registers, which go up to 128 bits. There's a fixed number of registers in the architecture. So this is the thing that's somewhat different than other intermediate languages, which have infinite numbers of registers. So we fixed them. The numbers we fixed them out were 8 control, and the S, D, and Q registers share a pool of registers, which goes up to 128. So the formula up here, the S plus 2 times the number of double plus 4 times the number of quad has to be less than or equal to 128. This maps very well to the way that most people do hardware. If you think about an SoC instruction set on an x86 CPU, the single and the double, they share the same resources, and you can choose whether to get 2 single precision or a single double from the same register file. So because HSAIL is a very low-level instruction set, we're trying to map very closely to the hardware. We wanted a register file that represents the way that most hardware is built. The other key, because the register counts are fixed in HSAIL as opposed to being infinite, that means that the register allocation is going to be done before you get to HSAIL. And this is a key trade-off because register allocation turns out to be one of the more expensive pieces of compilation or finalization. So because we've taken that out of the final step, it really helps to meet our goals of making that finalizer thin and fast and very robust, because we're not trying to do fancy register allocation in that final step. Okay, SIMT execution model. So HSAIL presents what we call a SIMT execution model. That's single instruction, multiple thread. And what that means is that the programmer writes his program for a single thread of execution, like he's talking to one of those work items. And that's a beautiful thing from a programmer's perspective, because that's how programmers really like to think. They don't really want to do vectors or think about wider vectors when they're writing their program. What that means is that each work item appears to have its own program counter, even though that's not necessarily true in the hardware. Branch instructions look very natural. I can put in if statements and things like that, as opposed to having to manually predicate my code. Under the covers, most of the hardware, most of the GPU hardware and the things that run HSAIL use a SIMD style organization. So, single instruction, multiple data. What that means is there's really just one program counter, even though the programming model makes it look like you've got your own. And that's the way that SIMD is defined, right? One instruction does the exact same operation across a wide vector of data. The way that the hardware tends to do branches, therefore, is through predication. So the hardware will mask off part of that SIMD vector, and some of the lanes will be inactive. It'll run the instruction to implement the branch. SIMT has the advantages. It's a much easier model to program for as opposed to explicit vectors. It's a very natural path for mainstream programming models like Java, for example. People tend to program in a single thread of execution. The real key, though, here is that the SIMT model scales very well across vector hardware, across different vector widths. Because we haven't exposed the vector width to the programmer, that means that the same piece of code can run effectively on a vector width of 4 or 8 or 1 or 64, because the scaling there is done under the covers. It's not exposed directly to the programmer. And that's key for our portability goals, because if you look at the members of the HSA Foundation, we all have different vector widths, and they really do range all the way from 1 up to 64. The trade-off there, in some cases, you can get better performance if you are aware of the vector. So HSAIL does provide some cross-lane operations that can allow you to recover some of the performance. And I've got a couple examples of those in a slide or two. Okay, so the wavefront is kind of the way that HSAIL exposes this vector width. So HSAIL defines a wavefront. This is really the width of this vector that I just talked about. It can range in the spec. It's allowed to range all the way from 1 to 64. Example here, lanes in the wavefront can be either active or inactive. So if we had a branch instruction or we're looking at a condition, some of the condition would be true for some of the work items. So those lanes would be active here. On the else statement, the other half of the lanes would be active. So the way the hardware would execute this is typically with these masking operations where some would be active the first time, the other set would be active on the next iteration. There is a trade-off here. So like I said, you can program at the wavefront level or wavefront-aware programming. In some cases, that helps you to get peak performance. But the trade-off is you're giving up the portability, because once you make that trade-off, now you're starting to embed this knowledge of the wavefront, knowledge of the target vector width inside your code. But sometimes that's the trade-off that people are willing to make. That portability is not that important to them. They would rather go for peak performance. So I had a couple examples of the cross-lane operations that are provided in the HSAIL instruction set. The first one is something called count lane. So what we're going to do is look across the wavefront, and we give it a register. In this case, it's S6. So I'm going to look at all the S6s from the other work items in my wavefront, and I'm going to count the number of those S6s that are not equal to 0. And every work item will get the same answer. So the point is we're taking advantage of some possible hardware acceleration that is able to, because these work items are in the same wavefront, there's some hardware that allows us to do this kind of operation more efficiently than, say, going through group memory. Another example is a count up lane. So this one is looking at the actual, the number of wavefronts that are active. And every work item here is going to get a different answer. So it's going to start from the first work item in the wavefront and kind of sequentially count as it goes across. So every work item will get potentially a different answer that indicates the number of earlier work items that are active. And this could be useful for a compaction algorithm where you're trying to figure out how many are active, where exactly should I write my slot, should I write my answer into some output array, for example. Okay, HSAIL modes. So we worked on this spec in the working group for several months. And one of the things that we really tried to do was to limit the number of available modes and options. You know, it's very easy in a working group to just add an option for everything that makes everybody in the working group happy because your mode is supported, but it does make life more difficult for developers and programmers because now you've got this kind of wide variety of different target platforms that you have to support with a bunch of different options. So we really tried to focus on making things easier for the programmers in the long term and really try to minimize the number of options and different features that could be parameterized. There were two modes that survived all those discussions, and so I wanted to describe those. The first one was the machine models. So the machine model refers to basically the address and the data width. And we have a small model, which is 32-bit pointers and 32-bit data. We also have a large model, which is 64-bit pointers, and the data can either be 32-bit or 64-bit. So this maps very well to the way that CPU instruction set have evolved over the last 5 to 10 years or so. Vendors can support one or both of these modes. 32-bit saves hardware. It can give you smaller pointers, which can give you higher performance. The larger model, very useful for accessing lots and lots of data, more than 2 gigs or more than 4 gigs of data. So that was one mode. The other one that we have is related to floating point. We have a base and a full profile, and they have different requirements for the accuracy and the rounding and the different floating point characteristics. The base profile, in some cases, it's very expensive to provide full IEEE support with all the different options, and vendor hardware, in some markets, it's not really necessary. So that's the reason for the existence of the base profile. I'm not sure if you can see this or not. This kind of goes through, I wanted to provide a little bit more detail on what exactly are the features that are different between the models. So the first one up here is the addressing modes. So both of the models support both the small and the large addressing modes. It's possible to do load store conversion of floating point values for all three types for both models, both base and full. All the operations are supported in both models, so we don't have operations that only work in the full model, for example. They both support F16 support, which is IEEE 754 better accuracy. F64 support, so this is something that does have a hardware cost. And so F64 support is allowed in the full, or it is required in the full model, and it's not allowed in the base model. The precision for the common math operations, add, mul, and subtract, so that's fully accurate in both models. We do see some differences in divide and square root. So in the base model, those have relaxed accuracy requirements, where in the full model, they're down to half ULP. The rounding modes are also different. So the base model only supports the nearest rounding model, whereas the full model supports all 4 possible HSAIL rounding models. Some differences in subnormals. So subnormals are always flushed to 0 in the base model. NAND payloads are propagated differently. FMA instruction is not required in the base model, but it is required in full. And some differences in the way that exceptions are reported. So fundamentally, like I said, the base model was kind of driven by a desire by some members to provide a smaller subset of floating point, whereas the full model is targeted at the richest possible HPC style applications. Okay, I wanted to show an example to kind of give a flavor for how HSAIL fits into a real programming model. I wanted to start with Java here. How many people here would consider themselves to be Java developers? Okay, there's not very many hands. The rest of the world really programs in Java. Java is consistently one of the top 1 or 2 programming models in the world. And the reason for that is not because it's not really targeted at peak performance. It's a high productivity language, right? It's managed code. There's garbage collection. That's the trade-off that a lot of the rest of the world is making. What would be really cool is if we could let people program in Java and deliver to them the benefits of this GPU acceleration. So what I want to do is talk through an example in Java. In this case, the code that we're going to show does a pretty simple calculation. We've got a set of players. The players are part of a team. What we're going to do is go through each player and compute the percentage of the team scores that were achieved by this particular player. So if we look at the class here, I have a Java class which has 3 private member variables. So the first one is the team that the player is a member of. A key point here is that this is an object reference, which means it's a pointer. So this is a pointer to the team. So we're going to use this pointer effectively on the host and the GPU. The private int scores, the second line here. So this is just the number of scores that were achieved by this particular player. And then the floating point percentage of team scores, that's what we're going to fill in after we run the calculation. These 3 public things, these are just the accessors to get access to the variables inside the Java class. I didn't show the team class here, but you can imagine what it's going to look like. It's going to be another class. It's also going to have a scores variable, which is the total scores achieved by that team. We didn't show the code here, but we have to assume that this array called all players is an initialized array of all the players in the league. So you can imagine this is an array of pointers. Now the pointers go to the Java heap, which means it's not required to be packed into memory. These objects could be scattered anywhere in the Java heap. So we're not requiring that they be repacked. This stream line here, stream is essentially a way to access a new feature of Java 8, which gives you parallel iteration capability. So the stream is not a new data structure. So we're not copying or repacking the data when we create this stream line here. Okay, and then the for each, this is actually the kernel that I'm going to want to run on every single one of these players. And we're using the lambda syntax here. Essentially what this says is create a variable p that points to some variable, some player that's in the array, and then run this small sequence of code on that player. And the code here, if we read through it line by line, the team scores is going to read from the team variable, which again is a pointer, to get the number of scores achieved by the team. And then I'm going to do a little bit of math here to divide the number of scores I have by the team scores, and I'm going to store that into the player array. So this is the HSAIL. Now the HSAIL here is just for the piece of code in the for each, just the lambda that's in the for each. The rest of the code would be run on the host. That would go through a standard compilation flow that went from Java to the Java bytecode to the host CPU. This code was generated from the Java bytecode generating HSAIL. And if we look at a couple of the highlights here, the first line of code here shows the version statement. So this is 0.95. This is the version of the spec that we publicly released a few months ago. It's using the full profile, so it gives me access to full numerical capabilities, and it's using the large addressing model, which means I can use 64-bit data, 64-bit pointer. There's a comment here, static method hotspots is coming out of a modified version of the hotspot JVM. Kernel starts the kernel definition, and we're defining the kernel's name is run. We have a single argument to the kernel here. So we've defined a kernel argument, which is called arg0. This is going to be the pointer to the array of player pointers. Then line 6 here, I'm loading that pointer using from the current, loading that pointer from the current arg segment into a variable. This work item absolute ID function. So this is a built-in HSAIL function which tells me which work item I'm going to run the code on. So in this case, it's going to tell me which player I'm going to go index. The math here on lines 9 through 12. So this is doing, basically it's doing a little bit of math to figure out from that base pointer using the work item absolute ID to do the indexing into the array to figure out exactly which pointer I am. The other thing I wanted to point out, if we get down to line 19 here, this is the one that's actually doing that pointer indirection from the team. So using standard HSAIL, I've passed in a data structure which contains a pointer, and I'm using a regular HSAIL instruction off of that to dereference the team, get the scores there, and do this computation. So kind of stepping back from the details of the HSAIL, a couple really cool things about this. The first one is, this is in Java, so we're not talking about OpenCL or a dedicated compute language. We're really talking about this dream that I laid out on the first introduction slide, where I'm able to take the power and the benefit of GPU computing and bring that to a mainstream programming language. If we go back and look at this code, this is standard Java 8. There's no special language. It's really just what exactly I described was the goal, where the programmer is using a language he's familiar with, and he's just marked the parallel region that he wants to run on the GPU, and he's done it with this for each statement in the Lambda, which are already natural concepts of Java 8. And the other thing that's really powerful is we're using a data structure that contains a pointer. We're taking advantage of the hardware that exists on these HSA devices, and through the language and the support that's built through the compiler infrastructure, we're able to take pointer-containing data structures and use those efficiently through HSAIL. Okay, I wanted to go back to my slide where I was talking about the relationship of HSAIL and SPIR and where those fit into the compilation stack, and go through a comparison between HSAIL and SPIR. So SPIR is an intermediate language that was announced by Kronos about a month or so ago, maybe 2 months ago. And it sits a little bit higher level in the compilation stack than HSAIL does. Some of the key difference, if we look at the intended users for HSAIL, we see HSAIL is really targeted for compiler vendors who want to control the whole compilation stack. Because you're so close to the final hardware, you can do your own register allocation, you can do your own optimizations. It really gives the compiler a lot of control over the code that's generated. SPIR is it's a quicker target because it comes right out of LLVM, so you can kind of get up and running faster. And there's also a wider variety of hardware that's addressed by SPIR. SPIR, because it's higher level, has code generators for FPGAs, for example. That's not really a target for HSAIL. The IR is for HSAIL is very, very low. It's really just above the instruction set, whereas SPIR is a bit higher in the compilation stack. It's up near LLVM IR. The backend code generation for HSAIL is the thin, fast, and robust one because it's very close to the ISA, whereas SPIR has a much more flexible model. You can do lots of optimizations between SPIR and the target hardware, including register allocation because the registers are infinite in the SPIR model. So we've got some other contrasting details here. There's binary formats for both of them. They both have code generators for LLVM, so you can get from LLVM to HSAIL. That's also true of SPIR. Different targets on the back end. The memory model, Ben Gaster is going to talk about that in great length in a few minutes here when we get back from the break. HSAIL's memory model is very well defined. It's relaxed consistency. We have acquire release. The OpenCL memory, the SPIR memory model is really kind of mapped to what's supported by OpenCL 1.2. So some differences between the intermediate languages. I think the key point here is that they really complement each other. They fit into, SPIR fits into a high level in the compilation stack, and HSAIL is really a later phase in the compilation, closer to the ISA that's generated. Okay, we're supposed to be done at 10:40. I think I'm on my last slide. All right, we're in good shape. So let me kind of summarize with some of the key points here. I've covered a bunch of different topics. If we summarize HSAIL, the key point is to think about really where is it in the compilation stack, and it's near the end. So what that enables is this thin, fast, robust finalizer. Thin, there's not a lot of work that's done there, and it runs very quickly. Register allocation is done before we get to that phase. Portable, so there's really two pretty different things that I mean about portable. So one is, because of the foundation, there's a number of different companies that have signed up to support HSAIL. So it's got different possible paths to get to all the different hardware that's out there. The other is the design of the intermediate language. So the SIMT nature and the fact that we haven't encoded architecture details like the vector width of the machine enables it to be portable across all this different hardware. Complements OpenCL, so we just talked through the differences in the compilation stack and how HSAIL is very close to the ISA. And the final point here, it supports the shared virtual memory and these platform atomics. And so these are the characteristics of the hardware, the HSA hardware that HSAIL is designed to run on, are fundamentally supported by the HSAIL instruction set. HSA is going to bring GPU programming to mainstream programming models, and that's really what we're trying to do here. The shared and coherent memory that's part of the platform, so that bridges this problem that I mentioned earlier where the accelerator is far away and you have to copy your data back and forth. We're able to take these inherent benefits of GPU computing. It is faster, it is power efficient. We're able to make it easier to program. HSAIL is kind of the glue inside the programming languages that lets the high-level model generate HSAIL and get to all these different machines. And then finally, the Java example. So I already kind of went through this summary, but really cool that we're taking an unmodified programming language and able to get the benefits of parallel computing there. And then finally, we're able to take these pointers. And I can't stress enough how much that's a barrier today and how much HSAIL and HSA are really going to change that. If you can take these pointer-containing data structures and transparently use those on the CPU and the GPU, it really does change the way that people program GPUs and make it much, much easier. It starts to make GPU computing look like how people do CPU programming. And so I think HSA is really much closer to a CPU programming model than it is to the OpenCL and the way that people have programmed GPUs in the past. Okay, last slide here. So a bunch of the tools that I talked about in the specifications are actually available now. So the first one is the HSA Programmer's Reference Manual, which I call the HSAIL specification. So links here, you can download the 0.95 version of that specification and look at it. Some of the tools are available. So for HSAIL, there's an assembler and a disassembler. There's also an instruction set simulator for HSAIL that's available online. We also have a code generator for LLVM that is coming soon. So that will output both HSAIL and Brig from LLVM. And then the Java compiler that I showed here is actually not just functioning, but actually the pieces of it are publicly available. So if you look at the Sumatra project, or the Graal project is the name of the tool that we're using, I've provided the links to that as well. And that is it. With that, I will turn it back to the organizer. We'll go straight to the break.
No, we'll have questions.
Okay, I'm sorry. We'll take questions now.
Make sure, come up to the microphone when you have questions, please.
Yes.
Tadao Nakamura Kurchips Conference Series. I will reconfirm that your intermediate language is SIL, okay? That consists of instructions of virtual instruction set architecture.
Right.
If so, could you tell me the relation between instructions at each level, one-to-one? Virtual instruction set architecture language instruction correspond to the number of the instructions.
It's asking, is there a one-to-one relationship between an HSAIL instruction and a hardware instruction?
Right. It's not required. In some cases there will be. So for example, I showed add instructions. Those would typically, a single HSAIL add instruction would map to a single ISA add instruction. But you could imagine sequences of several instructions. It could be more complicated. Some of the cross-lane instructions that I showed, those could map to multiple hardware instructions. Recall, we're targeting a wide variety of different hardware, so you might even see differences between implementations, where on some hardware, there's a single instruction, on other hardware, multiple instructions are required.
Okay, that is why I asked you this, because you emphasized, especially for parallel compute. Therefore, I asked. Thank you.
Okay.
Hi, I'm Gary Brown with Cadence. I wanted to ask, it seems like the main thrust of HSA is bringing CPUs, GPUs, different cores into a very unified kind of programming, making it easier to program. It's a very fascinating topic. And I was wondering, for the class of algorithms, video signal processing or image signal processing that are typically not as efficient on GPUs, where they're more efficient on other kinds of hardware, such as imaging DSPs, are you trying to bring them under the fold as well, or is it really just focused on the CPU and GPU?
Yeah, no, we are trying to, we will bring those into the fold as well, right? So you're absolutely correct there. There are always going to be a class of algorithms where there is a better machine that can be matched to that particular algorithm or subset of algorithms. If we take the example of an imaging digital signal processor, it would still benefit from a unified address space, from coherency, from being able to do user mode dispatch and have the application queue the work directly to the hardware and not go through a driver. It'll still benefit from quality of service. So that's what I meant when I said we started with GPU compute and made sure that what we were designing and architecting for the platform would work across a range of accelerators. Now, the HSAIL virtual instruction set is particular to parallel processing. I could imagine a class of DSPs that would execute HSAIL. I could imagine a much broader class of DSPs where HSAIL would not be appropriate, and we may well develop a different intermediate layer to target a particular class of DSPs efficiently. Or you could imagine a case where a range of DSPs appear in the ecosystem that all share the HSA system architecture, flat address space, quality of service, user mode dispatch, but they each have their own tool chain. Right? So yeah, there's a lot of aspects of this architecture that go broad. Yep.
So I've been told we're eating into the break time, so we should take one more question, and Phil and I will be available during the break to take more.
Yeah, that's fair.
Okay.
Hi, John Montrim, NVIDIA. The center of gravity of HSA seems to be around SoCs, or at least integrated GPUs and CPUs. Has the consortium kept up with the progress that you're reporting here with respect to discrete GPU and CPU systems? And would, in particular, something like platform-level atomics comes to mind, where that might be problematic, especially if you had, say, an Intel processor and an AMD or an NVIDIA GPU. Are you as far along with discrete?
We've looked at that extensively, and what we see is that, the HSA is defined as a whole, is all about optimizing for the SoC and ensuring that programs in that environment can be written much more easily and be much, power efficient and performant. In doing that, we've noticed several things. First of all, there are parts of this architecture that are applicable to discrete GPUs, and discrete GPUs will benefit from them. For instance, the discrete GPU being able to operate directly into system memory, into pageable system memory, with the same addresses, and so forth. We already see discrete GPUs expanding their instruction set to be able to do these high-level language features like virtual methods and throwing exceptions. However, there are some features where discrete GPUs will be challenged, such as platform atomics and full memory coherency. And so maybe we find that balance, right, where for HSA compliance, everything has to be together, although there are different ways you could implement a microarchitectural solution to be HSA compliant without that constraint. And discrete GPUs will benefit from the subset of the architecture that makes sense for those programs. And of course, when there are workloads where the memory footprint of the working set is small and the actual size of the programming kernels is large, a discrete GPU would be a better match for that workload and would benefit from pageable access to system memory. But we don't expect discrete GPUs to be HSA compliant. Okay, with that, we'll go to break. I think we're going to start at 11:10, so you'll still get your full 20 minutes. And as Ben said, we'll hang out during the break if people have other questions. Thank you.
Thank you.
Welcome to the second part of the HSA tutorial today. And my name is Ben Gaster. I'm from Qualcomm, and I'm going to be talking about the HSA Memory Model. And then Ian is going to follow me. I'll take some few questions at the end, and then Ian will follow with about the queuing model that Phil introduced at the beginning. Okay, so I'm going to cover three main sections. I'm going to talk about the HSA Memory Model, motivate the design, and highlight some of its key benefits and aspects of it. And I want to tie it into just recently OpenCL 2 was announced and provisionally published. And I'm going to tie it in to the fact that it also has a memory model. And there are some nice correspondences between these two things. And I'll talk about a little bit how they differ from some of the memory models of Java and C++ that we've seen before. And then finally, I'm going to talk about just a simple example. There's some code in there. Maybe you can look at that afterwards, but just kind of highlight, why would you want a memory model and why would it be useful, and how HSA will allow you to address that. So, okay. So there are really three kind of key areas when you're defining models for these systems, and we thought about for HSA. In particular, there's the memory model, and it specifies safety. Can a work item prevent others from progressing with respect to visibility of loads and stores? And I'll talk about what that means in a minute. And this is going to be the focus of this part of the tutorial. There's other parts, and in particular, there's the execution model, which specifies liveness. Can work items prevent others from progressing? And that was what Ben Sander already talked about in his session on HSAIL. And of course, this is all about performance, right? We want to be able to enable very high performance applications. What's the point in offloading to a GPU if you don't care about performance? And for that, you'd have a performance model, and that kind of specifies the larger picture. You start talking about caches, or when you think about GPUs and vector-based machines, branch divergence is a very important thing. Now, that's really beyond the scope of what HSA defines itself, because that comes down to particular implementations. HSA is never going to define the size of a cache or the associativity or things like that. And so that's beyond the scope of anything that we talk about in these tutorials today. Okay, so the problem that I'm going to look at, and what this talk is all about, is that if we have some memory locations, A, B, and some other ones, and let's assume just for the duration of this tutorial that they're all initialized at the start of the program to 0, just for simplicity, what we really want to know, what the real problem is here, is that in this, let me just check out this laser, in this little bit of C program here, we have, we're setting this A equal to 1, and then we're defining some variable X, and we're reading it from B. And on the other side, we're doing exactly the opposite. We're writing B equal to 1, and then we're defining some variable Y, and we're reading from A. And in HSAIL, this could be represented as these two programs. You assume that these are two separate threads. In HSAIL, we call these work items, as Ben has already talked about. And of course, we're going to assign a register now and so forth. So here, we're just going to put this temporary into S1, as you'd expect. But particularly interesting here is that we have the store, which is storing to A. You see that we've got the address of A here, and we're storing S1. And then we're loading, X is being register allocated to S2 here. And we're going to load from B, as you'd expect. And conversely, on the other side, we have this. Now, the critical question that we're trying to address here is, what are the values of S2 and S4 after execution? That's what we want to be able to reason about in a sensible way and deduce a result. And as I say, just marking again here, A and B are initialized. Well, the values at the address pointed to by A and B are initialized to 0, just for simplicity of all the later examples I'm going to go through. Okay, well, the memory model, it tells us, it defines the visibility of writes to memory at any given point in time. And so we should be able to reason about the execution of those programs and how they're sequenced together to get a reasonable idea of what the result may be. Now, it will depend on the type of memory model, which we'll talk about in a minute, what is the set of valid possible executions. Some may be valid in one memory model implementation, and some may not be defined. And this is what this talk is going to be all about. What are valid in HSA's memory model and what is not. And sometimes you'll find that a lot is valid, because it actually turns out to be a very relaxed model. And of course, in any real program, you want to be able to reason at certain points that when I see this value, then all my previous values that are written by the guy that wrote this value are also visible and things like that. And so we'll talk about how to constrain HSAIL programs and executions such that you can reason about it in a sensible way. Okay, so before doing that, and I think that this is important, and anyone who's familiar with memory models over the last 20 years will be familiar with the work of Sarita Advar. And she described these things which she called the 3 Ps. So no, this is not really to do with me, but I wanted to point them out. And in particular, programmability. A good model should make it relatively easy. I think it all depends on your capability and how much you've learned. Easy to write multi-work item programs. These multi-work items are running concurrently, and such that you can reason about them and intuitively write them sensibly. Of course, as I said at the beginning, all of this stuff's to do with performance. And so any good model, I think, should facilitate high performance implementations at reasonable power. And when we talk about performance, I really think it's important to think about power, and the cost here, so that's very important. And it has some real design trade-offs in the hardware when we build these things that means that we don't necessarily go for the simplest model. We trade these three things off. And the other one is portability. A good model should be widely available and on different hardwares and different platforms, and it should be backwards compatible with whatever we do in the future. And so, these are the three things. And as I say, Sarita defined these in her PhD thesis, at least in 1993. Maybe she published them before, I don't know. But these turn out to be important when we looked at the design and the definition of the HSA memory model. And in particular, I noticed, the common, most standard one that people talk about is this notion of sequential consistency, originally introduced by Lamport in 1979. And it says that a single processor is sequentially consistent if the result of an execution is the same as if the operations have been executed in order specified by the program. So basically, you might have these two threads, but you interleave them together, so you're going to end up with potentially different execution orders. But inside a single thread, those memory operations stay in a consistent, well-defined order. And this means that you can think about this in terms of hardware and how you might implement this simply by having some guy registering these are the different cores accessing, and each one we're going to select at a different point the instructions from this guy to execute, or the instructions from this guy and this guy, or this girl over here. And what we're saying is that these different selections will allow these to be sequenced in different ways in execution orders, but within this locks here, they stay in order. And so it's quite easy to reason about your program from a single thread-based execution. And the trouble with all that is that that's really great in theory, and it turns out it's pretty difficult to implement that to meet the performance goal, at least to date. There is some research that's showing that maybe it's possible. But so many hardwares, and let's take ARM v7 as an example of something that I get to work on within Qualcomm, and that has quite a relaxed memory model, very, very relaxed. It allows it allows loads and stores within a single thread to be reordered quite extensively, and that's assuming they're to different addresses. And so we need to think about that. And so you end up with this whirlwind of chaos that's going on inside these things, and I'll talk about what that means in a minute. But in particular, if you had a sequential consistent based execution, we'll get some interleaving here. I've marked these as being blue on this side and work item 1 as being orange or red, depending which way you can see here. And what you can see is that whilst we can interleave the different colors with blue and red and orange or whatever, the actual operations from the that should be a store, but anyway, that one should be a store. You can see are not reordered because, so if you take this blue one over here, the move, the store, and the load, that should be, sorry about that, would all appear in order and cannot be reordered. That was a typo on the slide about that. But, as I said before, what about the actual hardware? We've talked about that a little bit, that I already showed the diagram with the whirling tornado and ARM v7 being more relaxed. Well, sequentially consistency, I think most of us at least would argue that it's reasonably easy to understand, but it limits the potential optimizations. For example, if you have a store and a load within a single thread and they're to different addresses, then it really doesn't matter which order you execute those in. The hardware should be allowed. It speculatively executes. It may be able to resolve something quicker than another and start to do an evaluation of some intermediate result based on those loads or stores. And so we want to be able to relax that. Hardwares really want to be able to do many things. And in particular, even the most, if you look at the most common hardwares today, which I would say, x86 implements a thing called total stored ordering, which allows work items to see its own stores or potentially work items running on the same core early. Basically that you can query and get the store that's been put into the buffer. Or ARM and Power, for example, are based on what's called the relaxed consistency model, often called XC. in this terms. And more generally here, we can arbitrarily reorder loads and stores. So in TSO, you can only reorder stores, where in XC, you can reorder almost everything, assuming that it's to a different address, even within the same thread. And so that particularly means that same work items can see stores early running on the same cache, say, for example. And to start to see where this has an impact, you can look at this from a relaxed consistency. Our same example over here, again, starting with work item 0 and work item 1. And you can see that now all the loads have moved above all the stores. And so where before we could never get this execution where S2 equals 0 and S4 equals 0, it's completely reasonable now because, of course, the two loads have moved before the stores. And now it's pretty clear that we haven't got a sequential consistent-based execution because the loads have been reordered on here and here. And so with respect to program order, we've actually reordered the loads before the stores. And of course, completely valid because they're two different addresses. And so that would make sense from an optimization point of view. However, it can be difficult from a from a reasoning point of view. You know, if you're the programmer and you want to reason about what to expect at a certain time, and particularly once you have more than one thread looking at these stores, and you might want to build up what's called a causality rule, where you do a store here, it does a read, and then it does over here, it does a write of another value, and this work item over here would read that store from work item 0 and would assume that it can read the store from work item 1 as well if it sees the certain value. And so, you know, this is the transitivity that you might want to get from something that sequential consistency gives you quite nicely. Okay, but before we talk about how we can get back to sequential consistency, because don't worry, we will get back to it, because it's easy. What about our 3 Ps? You know, Sarita defined the 3 Ps. She talked about programmability. Well, I think it's probably fair to say that XC is pretty hard for programmers to reason about. If you've ever written built a lock-free data structure or something using relaxed atomics and fences, it is a really tricky business, right? And some of the best people in the world, when they were developing C++11, for example, someone published a lock-free algorithm using fences, and this was one of the persons who worked on the specification. Is a really smart guy, and it had 3 errors in it discovered by other people, and the blog had to be updated and going. And this is one of the world's experts, so it's not a trivial problem to get these things right. So I think it's fair. I think we can say that it's pretty hard to program, and to reason about these programs. Performance is great because the hardware and the compiler can do whatever it likes. Within reason, you can't reorder, with respect to the same address, but anything else is on. And this is really important. If you talk to people when they were developing the C++ and Java memory models, the compiler guys will come back saying, whoa, you said we can't do this reordering. No, we make use of that all the time. Of course I want to load a value into a register and to cache it there because, I want to, it's never modified during the loop, but it's only loaded, and so I want to be able to do that. So there's really important optimizations that you need to be able to enable. So performance is great. Portability, I think you could probably say it's pretty good too, because of course any program is you pretty much go at this point. There's very little constraints, and you can do whatever you like. And so we get 2 Ps, but we do really bad on this guy. And if we kind of weighted this to be 0, and then multiplied, we're going to get not going to do too well. And so that's pretty disappointing, because of course we really wanted to be able to have some sort of compromise between these 3 Ps to make it an efficient system. Well, it turns out, and I would have put the picture up here of my kids eating the cake, except they ate all the cake before I could take the picture of them. But really, the key thing is that my children and computer architects can have what they want. They can have their cake and eat it turns out. And this is not my work. This was work that was done 20 years ago by Sarita and others at Stanford here, who observed, actually, if we're careful and we think about and reason about certain points in our program, not all points, but certain points, and I'll talk about what those points are in a second, then actually we can allow the compiler and the hardware to have a lot of flexibility and still make it reasonable to reason about our programs, to do that. And HSA takes advantage of this. What we do is we provide the ability to enable the programmer to reason, again, with relative intuitive model of SC while still achieving the benefits of XC. And you have to make some promises. The programmer has to make some guarantees, and I'll talk about what they are. But if you do that, then the hardware and the software can have their cake and eat it, the programmer, and I think it's a great observation. So What we do here, and again, this is not something that we invented in HSA. And that's one of the benefits, I think, is that HSA follows Java, C++, more recently OpenCL 2.0, to adopt what's called sequential consistency for data race 3 programming. And this was originally introduced by Sarita Advar and Mark Hill in 1990 in their paper at ISCA, I believe. I think. Yeah, there we go. And the key thing is that they define what's the notion of a data race. And this will be important for the rest of the talk, so we'll do that here. And a data race can occur when 2 or more work items, so we have, and they're concurrently executing, and they're looking at the same memory location, and at least one of them is a write. It doesn't matter what the other one is, and there are no interleaving operations. So imagine that we had the load and store on that other slide, the store from work item 0 and the load from work item 1, they could clash next to each other in the program order because we're just interleaving it with that little switch, and they could, and so that would be a data race, and that's a critical thing. In sequential consistency-based models, that wouldn't be a data race, and that we're defining that a data race, but we're going to allow that, we're going to relax that a little bit by saying that we won't let it be a data race if and only if there are synchronizing operations in between. So for example, if you had that store and then you had a fence which said that all stores before this fence had completed, and then you had the load, then it would be safe. It doesn't matter where that load happens across it, as long as it's a synchronizing load, to say that, okay, I'm going to make sure, all the stores are completed, I do the load, it's going to see that store, there's a guarantee there. And of course, I said all stores, so the really nice thing about that is that I then start to get this transitive property that we talked about before, And so what SC asks of the programmer is that you have to ensure that all programs are data race 3, and what I mean by that is that you need to make sure that there's enough synchronization, enough fences or other load and require, which I'll talk about in a minute, semantics, which Phil already highlighted. You need to make sure that they exist in your program so there's none of these unordered or loads and stores that can appear next to each other to the same memory location. And with that guarantee, implementers will assure that the execution of those programs, those data race 3 programs, will optimize, but will meet at the synchronization point. So the visibility, the guarantees that we talked about, you will get at those points. Anything else is fair game. In particular, if there's a data race that appears in your program, that program is undefined. The hardware can do whatever it likes, and the compiler and everything else. So it's a guarantee. It's a kind of contract that we make between the hardware and the software. And if you break that contract on either side, then it's all over. Okay. So to achieve that, there's a number of different models and different ways of doing this. Again, I'm going to return back to a model that was defined by the people from Stanford and also by Wisconsin, Sarita and co. And introduce a memory model that's called RCSC. So what we will say about that is that it's called release consistency. And in particular, it will allow us, there'll be fences and everything as well, but just in particular for this talk, I'm going to focus mostly on loads and stores. And what we're going to say is that a load can be annotated with a acquire, which says that all previous stores and everything would have completed before the acquire completes. And then the store release, all previous loads will happen. Sorry, actually what it says is the load acquires guarantees that any later loads will not happen until the load in question has completed. And so it allows, you can think about like taking a lock, for example. And then the store release, you can think of analogous of releasing a lock, says that all previous stores will have completed before this store completes. And this is from the same thread. Okay, so now you can imagine that if I'm writing a bunch of data, I want to communicate a flag. What I'll do is I'll just write the data out. I'll do a store release from that work item. When I see that that flag has been set by doing a load acquire in the other work item, then that they match up the values, I know that there's going to be a synchronization between those two, and I can safely read the other values from memory, the other stores that thread made, because we're going to get a transitive relation. And so this is not the end of the story. This isn't in some relaxed models, XC-based models, you can have other things. So C++, for example, implements data dependencies or address dependencies and other things which are implemented by this consume-based operator. And they allow some flexibility, and you can carry dependencies. But HSA does not do that. HSA sticks on the RC-SC model. And in particular, it's interesting to note that this has recently been adopted and proposed for the ARMv8 architecture as well. And earlier models, things like Alpha, adopted a similar or a slightly different model, and Itanium has something similar again. They're all different trade-offs and different things are allowed. And we decided in HSA that this was the right choice because we think it maps efficiently to how we expect most programmers will develop Java, C++-based applications, OpenCL-based applications, and whilst giving the flexibility to the hardware. Now, there are definitely some hardware implementations. So for ARMv7, for example, that supports dependencies, address dependencies, and other dependencies that aren't easily accessible directly from HSA. But at this point, we haven't seen a real benefit from doing that. And however, I think what is really critical is that we didn't stop there. It turned out that actually, because we want to go beyond what CPUs can do today, we want to do what GPUs and what DSPs can do. And as Ben had already introduced in his talk, HSAIL actually describes a set of memories. You know, he talked about this group memory, which is visible to a collection of work items that are grouped together into a work group. It turns out that you can actually extend data race 3, SC for data race 3, to what we call HRF, which is heterogeneous data race 3, where you can actually describe visibility with respect to these different memories. And I'll talk about that in a minute. We call it scopes. And that work was originally introduced at MSPC this year with a paper that I was on before, and is based and is the foundation for both actually the memory model that I'll talk about in HSA, but also for OpenCL 2.02, which I'll talk about in a bit. Okay, so how do we get back the sequential consistency execution that I showed in the previous slides before we had the relaxed model? Well, actually, you can get that back by simply adding a release to the store and acquire to the load, and vice versa. And it turns out that if you put every store has a release and every load has an acquire in your program, then effectively you get back to a sequentially consistent-based model. And that's true for release consistency-based. Now, that's not something that you'd necessarily want to do, and I think this is a really important point. The true of our model, true of OpenCL, C++, is that you really only ever want to synchronize, which is effectively what you're going to be doing here, and some of these databases, if you're actually doing communication. You know, if you're just going to be reading these values from the same thread and you're going to be doing it all the time, then don't put them synchronizing, because you're potentially stopping optimizations that could be performed. And so it's really when we have more than one work item and we want to synchronize, you know, between them. You know, in this case, we've only got this one, but potentially we could have any number of work items that are communicating and synchronizing between them. And of course, now that we've got these executions, you know, we can interleave them in all different ways. But what is critical here, you know, the store and the acquire, because we've got sequential consistency back here, there's no way that this load can move before the release. You know, the rules for acquire and release say that they can't move past each other in either direction. So that cannot happen. And there is a slight difference with that and the C++11 model, if you're familiar with that, where it does allow a little bit more flexibility with release and acquire, and they call what's implement processor consistency model. But anyway. So let's get back to what we meant. Sequential consistency for data race 3. 2 memory accesses participate in a data race if they access the same location. At least one accesses a store, and they can occur simultaneously, you know, so they appear next to each other in the interleaving. Now, that's what I defined as the standard sequential consistency for data race 3. It turns out that HSA, we're going to refine that a little bit, and it comes back to this notion of scopes or different memories that I talked about in visibility. And this is where we kind of, HSA and OpenCL 2, as I'll show, go beyond the memory models that have been defined for C++ and Java, and really allow us, I think, to introduce heterogeneous computing as a first-class citizen. You know, it's not just CPUs anymore, but potentially other devices which may have these different memories. Now, that's not to say you couldn't take advantage of that on the CPU too, but we didn't necessarily design it with that in mind initially, at least. So a program is data race 3 if no possible execution results in a data race. If there's a data race, then the program is undefined, and we don't really care about that, as you see. So sequential consistency for data race 3 programs is what you get back from the hardware. You're guaranteed that. But you need to avoid anything else, because anything else is undefined And whilst it may work on the underlying hardware that you're targeting, HSA memory model makes no guarantee that that is the case. So be warned. However, as I said, that this is the key difference here, is that when everything's just on a single memory and you're at a global level, then all you need to care about is that the non-synchronized operations, and one of them's a right, appear next to them in the total order, then you're in a bad place. However, this is actually not quite strong enough for HSA, and I'll go through why that is and what it is. But what we need to do is we need to go back. There's clocks not ticking. I realize. So I've still got 60 minutes. Great, perfect. Okay, it's just something to observe. If someone could give me a heads up, that'd be really helpful. Thanks. Okay, sorry about that. So here's the execution model that Ben put up. And he had some different things on the right-hand side. I can't quite remember, but I'm going to make this explicit here because what we care about is visibility, right? We care about those two values, those stores that happen, and what we see when we do the loads with respect to that. And for that, we care about the memories that are visible in the system and things. So in particular, we had this platform level scope. So this is basically the SVM, the full-blown, everything can see everything from anywhere in the system that's a HSA compatible agent. And so that all works well. But we also have device scope. So what I mean by that, and HSA calls this a component actually, but I put device here just for ease of communication. But here, we're really talking about work items that are all running on the same device, and they care about visibility. But maybe you don't care about making those writes visible beyond the device. And of course, we can group this. Ben talked about group memory, where you have a block of work items all put together. And there, maybe you're just communicating between those work items, and you don't really care about that data proliferating out beyond that. And of course, we can go right down to the wave scope, because here, we might want to just communicate through a few waves in a few work items packed into the same vector. So you can start to see that, synchronization can now be valid at any of these different levels, and which it wasn't true. Well, I suppose it is true in a model like C++, but you just have one level, right? And so you don't really care about the fact that there are potentially these different scopes. And so what we want to do is start to reason about scopes and communication by scopes. So what does that really mean? And why is data race 3, as defined by the original SC one, not enough? Well, let's imagine that we have this group. This is global up here, and these are two groups that are running together, and thread 1, thread 2, or work item 1, sorry, work item 2, work item 3, and work item 4. And the colorings, as you'd expect, so they're grouped together here. Now let's imagine that we're going to do this store release here. We store value of 1 into X. We do a store release. This happens to synchronize with this CAS-based operation where we're doing acquire release, and so it reads it, and it sees that the flag is good. And then I'm going to do a store release over here of to flag of 0. And then I'm going to compare and swap that here over here, with that. So what's the value of X? Now, if these are all threads all running in the same scope at the top level, then we'd absolutely assume that if this is the synchronizations that happen, we'd assume that by causality that X is going to be 1. The value that's read here would be 1. So, this comes back to the two ordering memory access and participate in the data race. If they access the same location, at least one is a store and can occur simultaneously. Well, these are great, right? Because these access the same memory location, but we've got synchronization operations, so we go by the fact that they're separated by synchronization. But, as I said, if we assume that these are all accessing the global platform scope, then everything's good. But imagine that these atomics were actually happening, or these operations were actually happening just within a work group scope. So these guys could communicate, but could this guy communicate? Well, that depends, right? So it really depends. Is this a data race? Maybe not, because we have synchronizations between each things. And that's a debate, and I'll come back to that in a minute and actually say that we think it is a data race if they're different scopes, but why? But would it be SC? And as I say, this really depends. And it comes down to be, the visibility that's implied by the causality of these two things. If this guy and these writes communicate at a wider scope, then you'd really expect that these guys are communicating at the wider scope, then everything should be great. And there'd be no data races, everything would be fine, and I would see 1. However, as I pointed out previously, there's these different scopes, right? These different memories, and I might not want to make those visible. I need to be able to reason about that. So what we do is we extend it. We extend the notion of sequential consistency, and we extend it to be for heterogeneous race 3. And I'll define what a heterogeneous race 3 is. To very similar to SC for data races for SC. In particular, they can access the same location. At least one accesses a store, just as we defined. Can occur simultaneously, clearly. They appear next to each other in the interleaving. Are not synchronized at enough scope. So even if there is a synchronization-based operation, that it doesn't guarantee that there won't be a data race. They actually have to be synchronized with enough scope. So in that case, that example I showed you before, here, it would be enough to, it would be enough to synchronize these things at the device level. That would be enough. But of course, you could synchronize them at the platform level. Now, you might not want to if you don't actually want these writes to be visible outside of the device. But that is a critical point, is that we want this flexibility to synchronize at different granularities of scope. And, So a program is heterogeneous race 3 if no possible execution results in a heterogeneous race. I just defined what a heterogeneous race here. So clearly you have to do enough scope. Sequential consistency for heterogeneous race programs is what you need to guarantee, and we'll avoid anything else, because otherwise you're going to get a bad behavior. So what do I mean by enough? Well, simply both threads synchronize using identical scope. Now, you could actually imagine a more flexible system here where you allow scopes to expand out when you're doing synchronization. But for HSA, and actually it turns out OpenCL 2, we decided that enough means identical scope. So it wouldn't matter in that previous example if they were both device or platform, but they would all have to be the same to guarantee synchronization, even though in theory you could have slightly different ones. So for example, here I've put workgroup synchronization here, and I've got workgroup over here. But we know that workgroup scope is constrained to the work items that are within the same work item, and over here too. And so here we have a different scope. So here we have a data race, and the result of the load of X is undefined, is all defined. Now, it is interesting, and again, not covered in HSA, but you could see that potential research and ideas to think about this is that this could effectively, if we did want to synchronize these two guys, this could synchronize at, say, platform, and this guy could synchronize at device. Now, would that be valid? Absolutely, it's not valid today in HSA, but you could imagine systems where that could be valid, and that's an interesting area of research still outstanding to do. But the conclusion here, this is bad, right? If you want to synchronize between two work groups, then you need to at least synchronize with enough scope, and that would be device or platform. And so you can't do that, not if you want to get the expected behavior. And so, for performance, you really want to use the smallest scope possible. What is safe in HSA? Well, the smallest scope that includes all of your producers and consumers of the shared data that you're sharing. So in the work group, it had to be device, So an implication of this, and it is a big implication, I think, is that producers and consumers must be known at synchronization time. The fact is that, you needed to know that those two work groups were going to synchronize with each other, and so you needed to at least band out to the scope of platform. The question comes, is this a valid assumption, And, well, that's an interesting question. So, we looked at lots of existing regular GPU workloads that exist today. And what normally happens in these is that you'll take some grid of computation, let's just say an image, say, for example. You're going to tile it in some way to partition it down into work groups. There's a million different ways of doing that, no real surprise here. And then, of course, as I talked about, you're going to communicate locally within that work group to produce an intermediate result. Imagine you're doing a reduction, say, for example, and each work group will generate a value that it will then have a global communication where they sum up those final values, for example. It's a typical reduction, parallel reduction. And of course, if you're doing something like parallel reduction, you'll repeat that n times to communicate locally because, you're dividing by power of 2, say, in your reduction. And then finally, you want to communicate those partial sums that you've done in your reduction, and you communicate them globally, right? So here you're going to be doing local synchronization, scoped at local. The final write, where you write that final value, you're going to do a store release to at least device, depending if you're doing it across devices or not. And then so you're going to communicate globally. And then maybe you're going to repeat the process. I don't know, you're doing some iterative-based algorithm which requires that. And so there you'd have M going back. And that's great, right? Because here you're communicating at the workgroup scope, and you're then doing a final release to platform scope or device scope, depending on which level you're communicating. Here, you're going to be communicating at that platform or device scope and going back in again, and you can start the iteration again. So that all works pretty well. So it's really well-defined regular data partitioning, well-defined regular synchronization patterns equals producers and consumers are really known. You know, you kind of know that the levels that this program, I described how you could break that down for a reduction and, you know, similar algorithms. However, there are some other algorithms. So, for example, irregular workloads that might not work so well, and I'll talk about that in a second. HSA works well for regular data parallel workloads. And what about irregular workloads? You know, and so we can absolutely support these in HSA today, but now, as I said, because the scopes are static, there's some refinement that you might need to make. The thing is, imagine you're doing a work stealing algorithm, for example, and you're generating something on one core, it generates a task, and then you want core 2, which is in a different part of the system, to just be able to take that and run that. Well, if you haven't synchronized the memory for that task at the right scope, then you are potentially not going to see those writes that happened on this core and in the loads that happened in this core. And so what you must do at this point is upgrade. You know, so you'd upgrade workgroup to platform, say, for example, and that would give you this one. We could have upgraded it to the device. It all depends on what you're trying to achieve. And here you can see that we put the modifier for the stores and atomic operations to be platform. Again, so you can always promote. And I think, you know, generally you can imagine developers, at least software developers, may put platform first and then optimize it as they go down and find their bottlenecks and say, oh, okay, I know that I need to do this in group memory, and so then I'll put a group-based synchronization and so forth. And it's very standard how you do composition for blocking-based algorithms, say, for example. So the critical seeds, and so in this case, we can see that the HSA memory model, because we've updated everything to platform, if these synchronize, then you will see 1 in S1 at this point, and you're guaranteed wherever that runs. And this workgroup could be running on a different device altogether. You know, it doesn't have to be. Okay, so I've given you an overview of the HSA memory model. I think we've kind of got to the core things. You know, we implement release consistency for heterogeneous race-free programs. And so what are the applications? You know, how does this work? You know, it's all great and well that we have this new architecture description. Assuming that implementations come along, we want to be able to implement and use memory programming models that exist today. And so one of the things that I've been focused on is OpenCL 2. It turns out has a memory model too, and which is great. And you know, can we map that efficiently onto HSA's memory model? And I'll talk about it a bit now. So the provisional specification was released at SIGGRAPH 13, and so just I suppose a month ago now, in July. And it's a huge, huge update to OpenCL. To account for, I suppose, evolving hardware landscape and emerging use cases. You know, there are more regular workloads appearing and things that we want to be able to do on these devices that we couldn't do. Well, at least we couldn't do in the last few generations, and you couldn't do in OpenCL. So some of those key features, shared virtual memory, including platform atomics. So that's a nice correspondence with HSA. A formally defined memory model based on C++11, C11. But it's extended to support scopes. So it's actually very similar to the model that's described here. The one difference, and I did mention it, I won't go, people who are familiar with it, is that the OpenCL has adopted processor consistency model rather than the release consistency. So it allows some slightly more reorderings with around the load, acquire, and store, release. But it doesn't adopt the full C++, the consume, and some of the other stuff. It's restricted, just like the HSA model is. It introduces generic address spaces, so you can think about this as similar to the flat address space that Ben talked about earlier. It allows you to subsume these other memories into a single address space. Of course, we want to be able to do device, and queue, because we want to be able to handle irregular workloads. So you can start to create work on the device now and queue it to itself. To handle this in an efficient manner, they have out-of-order device-side queuing model, which I'm not going to talk about here. And of course, to get your Ps, however complicated OpenCL is, it didn't want to make it more complicated by not being backwards compatible with 1.x, and it is. So 1.x memory model turns out to be anything but well-defined and is trivial to map. There's no orderings. There's just standard loads and stores. They actually turn out to be only guaranteed visibility within a kernel, within a work group. So we can just map those to HSA's load globals and store global, but with a work group scope. And atomic operations, now they can be either component-based scoping or work group-based scoping. You can define them. It's actually tricky and debatable whether you can define that explicitly in OpenCL today, but you can do it. And OpenCL has a barrier operation which allows you work items to wait for other work items in the same work group, and HSA has a similar thing, and here you define the scope to be work group. So it's a fairly straightforward mapping that we get. And as I say, the atomics are unordered in OpenCL, and so they just simply map to the unordered atomics in HSA. And so here there's no acquire release added to the atomic operations to provide an ordering. And I haven't shown fences here, but they'll be straightforward to map. OpenCL 2, it gets more interesting and more complicated, but as I said, it's actually a fairly straightforward mapping, and we can take unordered atomics, so specifically atomic operations which guarantee read-write coherency. You can map to the HSAIL's atomic load and atomic store, HSAs, and of course, OpenCL has scopes now, so we start to map it to the scopes, and we can do it on global or group memories. And it's a pretty straightforward mapping. You know, one thing that they do, they have full sequential consistency in C11 and in OpenCL 2, and so you can see the load, memory, order, sequential consistency, and we have to map that to be a fence rail scope, and then do the load afterwards, for example, for a load, to guarantee that nothing will move past the load operation, and can't move into the lock, for example. And it's fairly straightforward. I'm not going to go through the rest of it. The atomic operations map nicely to the atomic operations so when I read, modify, write, atomic operations map naturally to the HSA equivalents. That. And of course, as I said, we've got the memory scopes, and the OpenCL memory scopes map naturally to the HSA scopes. And so there's no real surprises there. And again, okay, so this is the last part of the talk, and I think I've just got about 5 minutes. Yeah, so I'm going to, so there's quite a lot of code in this section, and it wasn't my intention to walk through all in detail. It was actually the intention to make sure that I always get frustrated when you download slides, and then they have all this stuff, and you don't really get, all you got is a couple of bullet points, and you can't see it. So I put the code in so you could always look at it afterwards if you're really that way inclined. I suppose I'd probably read it. And, but I'm not going to go through the code in detail. But I did want to motivate, what is a good example? Why do we need a memory model in practice? It's all great. We've come up with all these lovely ideas, and all these languages propagating them. Well, I think, an important application here for memory consistency is in the development of concurrent data structures. That has lots of other application, but for me, and my interest has been in development of concurrent data structures. And in particular, I'm interested in algorithms that have certain guarantees around lock freeness or wait 3 or obstruction 3. These are all kind of slightly different levels of guarantees about progress between two different threads or progress of a particular thread making. And in particular, you could have something like a lock 3 algorithm that says that given enough time, at least one thread of the work items, or work items will make progress, And this is pretty tricky to implement in practice, it turns out, and you often have to have cooperating work items to help the other guy proceed and things like that. And that's great, but the algorithms don't always turn out to be the most efficient things in the world, and it can be tricky. But it turns out that there's this really nice notion of obstruction 3. And now, it doesn't provide all the lovely guarantees, but it does say, and you'll say this is a bad thing, but it does say that if a work item running in isolation will always be able to make progress. And now that's quite pretty good, right? Because if you know that your algorithm, you're not highly contended, it's not that likely, but you do want to be able to still guarantee mutual exclusion at the right points, then it turns out obstruction 3 can be pretty useful, and it doesn't have some of the complexities. And so that's actually what I'm going to talk about in a minute. But why? Why do we justify not just using locks or mutual exclusion? Now, I definitely think that there is the place for those things and the potential, but we've been looking at it, from this perspective. This is Qualcomm specifically here, and I'm sure others are doing similar things, but we had this emerging compute cluster. And, I've got our Adreno GPU on one side, we've got our Crates CPU sitting in the middle, and we've got the DSP which actually I believe will be talked about on Tuesday here, sitting on the other side, and they each want to communicate. Once we have this emerging thing, the fabric and memory controller, we have this shared virtual address space sitting on top of it, and we have platform-based atomics, say, for example, if we did, then, they're all going to want to communicate with each other. But let's say the hexagon takes this lock, right? It's going to be scheduled in some way that may not be controlled by a centralized high-level OS that's running on the crate, for example. And vice versa. What happens to the Adreno? How can they then do that? And again, the crate might then. What really happens is that we have a lot of different clock speeds, the different scheduling policies, and it's not clear. And I'm actually not saying that it's not possible, but it's not clear that the traditional mutual exclusion-based algorithms fit really well here. And it's not just an issue with NUMA-based memory system. You actually got, because these run the different policies of execution and clock speeds and everything, it's not even clear when something might get powered down. There are a lot of trade-offs to do. Whereas if you could provide some guarantee of progress independent of these other cores, then you might benefit from it. And so, I think, there's a lot of work to adapt existing concurrent data structures, developers new concurrent data structures. We're going to develop these things. I don't think necessarily one size or what's happened in the past will fit to this. There's a lot of work to do. But, and lock-based programming will still be important. I absolutely agree with that. But the key point I want to make is that whether it be lock-based or whether it be lock-free data structure or obstruction-free, the memory model is going to play an important fact. For some people, if you're just writing about locks, it's going to be the implementer of the locks. For the lock-free data structure or the obstruction-free data structure, it may be you. It may be the programmer that's writing those things, and doing that. Now, you may argue that it's going to be right down there at the bottom, just some system programmers, but I don't necessarily think that's the case. Certainly when you have so many threads and execution. And so I just wanted to highlight, the benefits of it here, and the rest of these slides develop a well-known obstruction-free DQ implementation. Maurice Hillary and others developed, I think, when they first published the notion of obstruction-free in 2003. And it's turned out, actually, we found some new use cases for double-ended queues, which I can't talk about today, but I think that it's a nice example and something that we are actually using in practice internally for things. It's a fairly straightforward data structure. It uses a fixed length circular-based queues, so it's bounded in a size at any time. And basically the idea is that you, at any given time, you have a set of invariants that's to do with the bounds inside the circular queue, and you have some set of null values. There's more than one. There's ln for the most left a null value, and then a dn, which is a dummy value, which allows you to handle the circular bit. If you weren't handling the circular, you wouldn't need the dn. You could just have the ln and rn. And then for the right null, you have values. So, basically, you always find in the queue, you have the right values. The rn will be here, and then you'll have your L values. So you have an ln and an rn. Or the ln rn could be replaced with a dn. And one of these variants have to be whole. You have to have at least one ln or dn and at least one dn or rn at a time. So basically, there's always a place you can always find where you're going to insert. And what you do, just for simplicity of the queue, you make sure it's double the size. You actually add 2 extra elements, and so you don't have to worry about not having that invariant hold when the queue's full. But that's very simple. But the critical thing is that you can access this queue from any end, from any thread, or work item at any time, concurrently. So you really do need some sort of consistency to make sure these things are visible to others, and it will appear across the whole system. So potentially, depending on how you're going to share this data structure, we might want to actually parameterize it by a scope. But I haven't done that at all in this, and just assumed a global scope. 5 minutes? Okay. Great. So anyway, so this would be what it would look like. I'm not going to talk about that. There's lots of code. I won't talk about that. But I did want to say one thing. And here, is these blue operations. I put them in there in the slides. You'll see them. And that's where we care about memory consistency. And you'll notice there isn't actually that many of them. And that's critical. And actually, I think it could probably be optimized more. I've just implemented it using sequential consistency semantics when I needed it because it was simpler. But you can see that there really isn't that many. Look, here's the blue one here. And there's a couple here. We have to do 2 cases because we need to test whether we've found a slot and whether it's actually free when we try to update it. And but that's it. The whole algorithm for the right pop can be implemented with just 2 cases and a an atomic load. So it's quite nice. So this is my last slide. And hopefully what I've got through today is that, the takeaways really, if you take away anything, HSA provides a powerful modern memory model. We've designed it with C++, Java in mind, but we've also thought about what the emerging hardware for these things are. I showed you Qualcomm's cluster, but I'm sure other people will have similar things too. OpenCL 2 introduces a new memory model. I showed that, it maps really well to HSA, and we believe it's a good choice, both for OpenCL and for HSA. And I think that, we will see it will start to enable a set of concurrent algorithms for emerging heterogeneous computing. We believe that this could really open up what's possible. And that's it. I'm ready to take questions. OK. Just 2 questions, if there is. Maybe there's not any.
Hi, I'm Sanjeev from Oracle. So what do you say about this memory model when you're incorporating those releasing stores and acquiring loads, about the scalability when you are scaling to multi-cores? What is the performance impact of those, and how much it impacts in terms of a programming model or the existing applications when it has to adapt to this particular memory model?
Well, so I think the memory model is designed specifically to map existing ones like Java and C++, right? And so if you're already using those memory models, I think it can map pretty efficiently. I think in terms of scalability, that's an interesting question. It will depend on the particular implementation, the hardware implementation. But I would like to say, again, I think that's one of the reasons we implemented scopes, was because I think, we have these different devices and it's cross. So it's not just about a core, but different devices spread out. And they may have different ways of achieving coherence with respect to the overall bus. And in that point, I think the scopes play a really big role, because it could be reasonably expensive if every guy in the system, where every girl is kind of synchronizing all the time to get down to this system. You're not going to be able to share them in some caches that are multiplex over certain cores. So I think that is critical for scalability. I think if you just do it randomly, just put platform everywhere, and you're just synchronizing all the time, then I suspect it's not going to scale that well. However, I would probably argue that that's true for a NUMA-based system today, right?
True, but does it work better than a lock-based, mutex exclusion-based schemes versus acquiring this? Because these are pretty much native load and store instructions which you are proposing here, and that means that either compiler has to take care, or you have somehow a way to extend it to an application which today is working with a lock-based.
Well, so I think for the locks, I think what would be the extended would be the implementation of those locks. So today you have a lock in C++, for example, mutex or something that's taken, and that's just implemented for to be shared across just the CPUs. And now, because we've introduced SVM, shared virtual memory, and you're synchronizing at the platform, that lock would automatically be usable, at least the underlying, values that it mutates, across all of those devices. So I don't see there's any difference there. There's nothing stopping you from using those.
What about the performance? If you go from, let's say, 4 cores to 8 cores to 12 cores, what happens if you compare it with a lock-based scheme versus your the load store mechanism which you have defined?
Well, I'm not sure. So I think it can be shown that locks don't scale that well beyond 4 or 8 cores, depending on the contention, right? You can always contrive examples, so it would depend on the application. I think the ordered load and stores, though, you would need to implement a lock. So a lock in C++ would be implemented underneath using the atomic loads and stores. There might just be a single memory location, and you're just implementing the mutex by incrementing and decrementing it. It would be the same thing, right? It's just that to the programmer, you're exposing just the interface of, get lock, release lock, and make them blocking. But underneath, someone has to implement that. Now, of course, on a CPU, you may get at least current CPUs, the OS may get involved and decide, okay, after a bit, you decide, okay, I'm going to do some back off. No, I'm going to go to the OS and block. And it may keep a list itself of people blocking. So there's different trade-offs. And now, for that kind of support, the OS would have to be extended and be aware of these other devices, potentially. But
so does the VM subsystem of the operating system needs to take into account this thing?
Yep, we can take that offline, yep. Should I take one more, or is that no? No, okay. It only says, I've got 27 seconds, it says.
I'm sure that says that.
Pardon?
That's counting over.
Oh, okay, it says I'm 35 seconds over.
Oh.
Damn. Go on. Yeah.
That's counting down to 1 o'clock.
Okay, it's counting down to 1.
Okay. Hello, my name is Ian Bratt. I'm an engineer at ARM, and I'm going to be talking about queuing, or what we internally within HSA call queuing. So queuing is a very overloaded term. If you talk to a lot of different people, each person will have a different idea of what queuing is. And in fact, when doing this talk, I realized that people can't even agree on how to spell queuing. So this is the way I spell it. And basically, what we mean by queuing is it's the mechanism for which one component in the system sends a job of work to another component in the system. So we're calling that the HSA Queuing Model. Okay, so let's look at kind of today's picture for how this happens. And we'll use the simple example of a GPU and an application running on the CPU, and then there's your operating system kind of sitting in the middle. So today, how do we send some work from the CPU to the GPU? Well, the first thing that happens is the application, it generates some data, and then it tells the operating system, hey, operating system, I generated some data. I want this to go to the GPU. So then we go into the operating system, and the operating system, then it has to actually do some various machinations to actually make sure the GPU can see that data. So maybe it's doing a copy from one region of memory to another. Maybe it's playing some remapping tricks, who knows. But at some point, it completes, and then it tells the application, yep, okay, your data has been transferred. At that point, the application is free to say, okay, now I want the GPU to run something and consume that data. So it tells the operating system to go and schedule the job. The operating system goes and issues the driver. Then the driver schedules a job for the GPU. And at this point here, the GPU can actually start doing real work. So the GPU does some real work. Then it finishes. And at this point, the GPU says, hey, I finished my work. We go back to the operating system, and the operating system says, oh, hey, there was an application waiting for the GPU to finish this work. I better tell that application that the GPU is done. So then the application wakes up, and the application, maybe it's consuming the results that the GPU generated, so it decides to read that memory. So then you have to tell the operating system to map that memory from the GPU back to the CPU. So then the operating system does some things. And then when the operating system is done mapping that memory, you're done. And the whole thing is just totally exhausting. So this is the state of the world today. And there's nothing wrong with this, but the reasons for a lot of these things are historical. And we know if we want to start using a GPU or other elements, so this doesn't have to be a GPU, it could be a signal processor or something else. If we want to start using these in a more generic environment, we have to fix this. We have to fix this somehow. So that's what I'm going to talk about. So in order to fix this problem of kind of high latency job dispatch, HSA defines essentially 4 architectural requirements for an implementation to satisfy in order to be kind of HSA compliant. So the first one is shared virtual memory. I'll talk about all 4 in detail. The first mechanism is shared virtual memory. The second is system coherency. And here I'm talking about actual true hardware cache coherency amongst the different agents in the system. Signaling mechanisms in order for one agent in the system to kind of wake up another agent or signal it. And then user mode access to queues. So these are the 4 architectural requirements that HSA specifies. And then the vendor is free to implement these things however the vendor wants to. So let's talk about the first one, shared virtual memory. So this is kind of the state of the world today. We have a CPU here, a GPU here, and both the CPU and the GPU might have their own virtual address spaces. And in the CPU case, while those virtual pages are mapped to physical pages, the GPU might have different virtual addresses mapped to the same physical page, like this case. There also might be another set of physical memory here that's just private to the GPU, that the GPU uses. So this is kind of where things are today. And having shared virtual memory, it takes us into this direction here, where we have a single virtual memory address space across the CPU and the GPU. And the mappings from virtual addresses to physical memory are consistent from the CPU and the GPU. Again, this doesn't have to be a GPU. It could be any HSA agent. We also have this physical memory up here. So it could be that maybe your GPU still does have its own private physical memory, but maybe it uses that for other applications, not really in the compute scenarios. And we're talking about the compute scenarios here for HSA. So this is what shared virtual memory picture looks like. What are the advantages of this? Well, a big one is that there are no mapping tricks. So the OS doesn't have to do any clever mapping to map different virtual addresses to the same physical addresses. There's no copying back and forth from one physical memory region to another region. A big one, of course, is that if you want to send some data between 2 agents, well, you just send a pointer. You don't send the data. Now, I'm an implementation guy, so I'll talk a little bit about the implications of this requirement. So what does this mean to somebody that actually wants to support shared virtual memory? Well, it means we have to have common page tables. So we have to have a common page table that's used on all the components in the system. And not just that, but you have to have the same interpretation. If one of the bits is a shareability bit, every agent in the system has to interpret that shareability bit the same. You have to have a common mechanism for address translation. So everyone needs to be servicing or translating virtual addresses to physical addresses the same way. And there needs to be a mechanism for handling faults. You need an idea of a process address space so that you can have multiple processes running within the same system. So you have a per process virtual address space. Okay, so let's go back and look at our original picture and having that shared virtual memory, how does this picture change? Well, we can move the OS out of the picture when it comes to copying memory back and forth or doing the memory mapping tricks between the CPU and the GPU. So that goes away. So we're getting there. Things are a little bit better, but there's still a long ways to go. So some more specifics about the HSA shared virtual memory requirement is that the minimum VA width is 48 bits for a 64-bit system, and it's 32 bits for a 32-bit system. HSA agents can reserve VA ranges for their internal use. All HSA agents, other than the host, must use the lowest privilege level. And you have to basically follow the same semantics. So read, write, you have to follow the same, everybody has to follow the same read, write semantics. Okay, so that was shared virtual memory. Remember I talked, there were 4 things. Well, now we're on to the second, cache coherency. So an architectural requirement for HSA is that data accesses to global memory, so this is the global memory segment, or we often call it the primary memory segment as well. These accesses are cache coherent, so the data is coherent without any explicit cache maintenance operations. So, well, what are the advantages of this? Well, I think everyone understands the advantages of shared memory programming. You get composability. So it's easy to take smaller programs, include them in bigger programs, which are included in then bigger programs if everybody's doing shared memory. You have reduced software complexity when communicating between agents. So anyone that's written shared memory programs knows it's actually quite tough to communicate with shared memory, but it's still easier than communicating without shared memory. So there is some reduced software complexity versus manually flushing caches and doing all sorts of crazy tricks. There's a low barrier to entry when porting software to HSA. So the majority of the world's code that's parallel code is shared memory. So when porting to HSA, it makes it easier. And of course, what are the implications on the implementation of this requirement? Well, it's pretty straightforward. You have to build hardware cache coherency. So that's a requirement for HSA. This, of course, can take many forms. HSA's job is not to specify the form for how you implement your coherency, but just that you implement it. So that's a requirement. So let's go back to our picture here. And let's see, how does this picture change if we have cache coherency? Well, on the application side now, when it's generating data that's consumed by the GPU, it doesn't have to do any cache flushing or any fancy tricks in order for that data to eventually make its way to the GPU. So things are getting better. We're still not there yet, but things are getting better. So some of the specifics around cache coherency that HSA requires is that it's not required for instruction memory. It only applies for the primary global memory type. And you can't do kind of tricks like have one agent map a page as read-only, and then another agent modify it and write it and expect that to show up to another agent that had it marked as read-only. So you have to be consistent. All right, so that was cache coherency. Now we'll talk about signaling. So signaling is an architectural requirement within HSA, essentially where we define signaling objects. And these signaling objects are created and destroyed through the HSA runtime APIs. So you create a signaling object through an HSA runtime, and then you can directly access the signaling object straight from your user mode code. So for example, you can signal a signaling object from user mode code, which will wake up anyone in the system that's waiting on it. You can query an object to see the state of the object, and you can wait on an object. So if you want to go to sleep until a flag gets set, you can wait on that flag. So what are the advantages of signaling? Well, it enables this asynchronous interrupt between different agents in the system without involving the kernel. This is a common idiom for work offload. People are pretty familiar with the idea of signaling. And importantly, it's a low power option. So it gives you a low power way of waiting for an event to happen. If you're waiting for a flag to get set, you could sit there and spin and constantly read the flag, waiting for it to go to 1, or you can just wait on it and then get woken up when it goes to 1 via a signal. So what are the implications of signaling? Well, we have to have some runtime support here for creating and destroying these signaling objects. And from an implementation perspective, this often kind of comes hand in hand with the cache coherency. So if you're implementing cache coherency, it's not that much bigger of a step to implement the signaling on top of existing cache coherency flows. Okay, so let's go back and look at our picture. And if we add signaling, well, remember this box here where the GPU, when it was done with its work, it would tell the operating system, and then the operating system would invoke the application on the CPU. Now we can get rid of that because the application can just wait on something being produced by the CPU, and it will get woken up automatically via the signal. So things are actually looking pretty good here. Ideally, we'd just like to be able to queue the job and have the job executed, but we still have this block here where we schedule the job on the GPU. Some more specifics on signaling. HSA architects some specific conditions, like equal, not equal, less than, greater than, or equal. There's no requirement against false positives for wait operations. So it is legal for a wait operation to return even if a value hasn't been signaled. The implication on the programmer there is that if they get woken up on a signal, they have to go and check the value and make sure it actually changed to what they were waiting for it to change to. The HSAIL atomic operations that Ben talked about earlier, those are all supported on the signaling objects. And these signaling objects are opaque to the programmer. So it's just a void star that you then perform operations on. The programmer doesn't know what the underlying implementation is. Okay, so let's talk about the fourth final requirement, user mode queuing. I'll introduce this and then I'll dive into it in a bit more detail. So what is user mode queuing? Well, this basically allows a user space application running in user mode to directly, without the OS intervening, in queue a job to be executed by another agent within the system. So sometimes I'll say job, but internally within HSA, we call them packets, a packet of work. Or a dispatch packet. So when we're talking about user mode queuing in this sense, we're saying I'm going to take a program that I want to execute, call it a packet, and I'm going to send it for another agent to actually go ahead and execute. So these queues, they're created and destroyed via the HSA runtime. Many agents can enqueue packets, and only a single agent can dequeue packets. And what's important here is that this sits on top of the shared virtual memory and the coherency. So those are kind of stepping stones to enable this user coherency, or user mode queuing, sorry. So the advantages of this, of course, is that you avoid involving the kernel or the OS or driver when you're dispatching work for an agent. So this is obviously much lower latency because you're not going into a different privilege level. You're not dealing with the operating system at all. So this can actually enable, hopefully, a finer granularity of offload. And of course, you can use standard memory protection mechanisms to basically guard communication with the different agents. So you just use shared memory protection for guarding these queues. What are the underlying implications of this? So the important one here is that this is architected. So this notion of a queue is architected. So this means that there's some queue structure, and the layout of that structure is architecturally defined. And we do this in a way that we try to also guarantee backward compatibility. And then packets are placed in this queue via an architected protocol. So this all needs to be architected so that the same code can work across multiple different HSA compliant devices or agents. So we'll talk more about that later, in particular the architecture of these different things. So going back to our original picture, if we have these user mode queues that allow an application to directly send a piece of work for the GPU to execute, we can remove the OS entirely from this picture. So now things look much better. And this is kind of what you want. So this is where we want to be. And this is enabled by the shared virtual memory, the cache coherency, the signaling, and those three architectural things combined with an architectural definition of queues and packets to basically do this. Okay, so when we're talking about the queuing, we call this the AQL, or Architected Queuing Language. And in particular, the queues. So what is the queue? I've been talking about the queue, but what is that? Is it something in hardware? Is it flip-flops? Who knows? Well, so what the queue is actually, it's just a shared memory queue. That's all it is. So the default queue within HSA allows multiple producers. So I have two producers here, and I have a single consumer. We also support a single producer, single consumer queue if you want to optimize your system and if that works for you. And what a queue consists of is really just storage for the packets. So that's some region in shared virtual memory that's cache coherent that you store the packets in. The queue then has a write index, a read index, so you know where to put packets in the queue and you know where to read them. And then what we actually store in here are packets. And we'll talk about the packets later, but this is an actual packet. It's not a pointer to a packet. It's the actual packet. So these queues are created and destroyed via the HSA runtime. And packets, the way they're placed in this queue is via an architected protocol. So the packet format is architected, and this queue, in terms of how it's laid out in memory, where the indices are, where the storage is, that's also architected. Okay. So packets are read and dispatched for execution from the queue in order, but they may complete in any order. So there are a few other, we have to have some architectural language in order for people to understand how to actually use these things and reason about whether or not their programs will deadlock or not. So there's no guarantee that more than one packet will be processed in parallel at a time. An implementation is free to process as many as at once, but there's no architectural guarantee that there's more than one. There may be many queues in the system, so it's really up to the implementation if they want to put a max on the number of queues, and a single agent can actually be consuming from several different queues. So you could have different queues for different classes of work. A packet processing agent can also enqueue packets. So because this is all done through standard shared virtual memory that's cache coherent, there's no reason an agent like a GPU that's taking a packet and executing it can't then in turn place packets back into a queue to be executed later, maybe by itself or maybe by another agent. Once a packet is enqueued, the producer that's placing the packet in the queue signals a doorbell. And the doorbell is one of our signaling objects. So consumers aren't required to wait on this doorbell, so they could instead be polling on the shared memory values. The doorbell's really just there as an optimization for low power. And it's important also that the signaling mechanism in this case, when you're placing a packet in the queue, the signaling mechanism is really meant to enable low power optimizations. It's not meant to be the synchronization mechanism. That's done through the shared memory. Okay, so here's a potential algorithm for how you would place a packet into a queue. This is a multi-producer agent that's putting packets into a queue, and this is in C++11, so I went and learned C++11 the other day to write this. And the important takeaway here, you shouldn't get too worried about the details, but the important takeaway is that it's just shared memory programming code. And in this case, it's C. So the first thing you do is you get the write offset of the queue, and then you basically check to make sure the queue isn't full. If it is full, in this case, we're spinning and waiting. You could instead maybe do a wait and go to sleep. Once the queue is no longer full, then you try to get a slot in the queue via an atomic compare and swap instruction. You try to get a spot in the queue. If you fail, you probably have to go back up to the top again. If you succeed, then you basically write the packet to the queue. And in this case, we copy over the full packet, and then we set the format field on the packet here. So this is basically that says what type of packet it is. We set that to a dispatch packet, and we do that with release semantics. So this is like what Ben talked about earlier. So this means I do these stores that are copying the packet over, and then I set the format field to dispatch only after all those previous stores are visible to all other agents in the system. So it's just like a normal shared memory queue. And then in this case, you ring a doorbell. You don't have to do this every time. You could maybe amortize ringing the doorbell if you want to do 10 packets at a time or 100 packets. But once you've enqueued a packet, you can ring a doorbell in case somebody's waiting on that something to show up into that queue. So on the consumer side, the code's a little bit simpler because this is just a single consumer. So the first thing you're doing here is you're just spinning if the queue is empty by looking at the packet that's at the head of the queue. And if it's invalid, well, you just wait for it to turn valid. So you're just spinning while empty. You don't have to be doing that. Instead, you could be waiting on a signal. Once it's no longer empty, you copy over the packet, and then you set it to invalid. And you do that, you set it to invalid, and then you change the read offset with release semantics. So this here guarantees that all of these stores above are visible before the read offset is changed, and the producers know that a packet has been pulled off. Okay, so that was the queue, and the important thing is that a queue is basically architecturally defined as a certain set of fields, and this lives in shared virtual memory and cache coherent memory, and it's created and destroyed via HSA runtimes. So now we'll talk about the packets. So there are two main types for the packets. There's the dispatch packet and the barrier packet, and the format for these packets are architected. Dispatch packet is the most common type of packet. So it contains, kind of what you would think it would contain. It contains a pointer to the kernel. In this case, the kernel is some instruction program to run. It contains a pointer to some arguments for the kernel. It contains the workgroup size and the grid size, like Ben already talked about earlier, and some other things. Additionally, packets contain a barrier flag, and what this barrier flag is used for is that it enforces the system to guarantee all preceding packets launched from that queue have completed before that packet starts. So it's a synchronization mechanism. If you have one packet that's consuming the results of packets produced, packets executed previously. So this is the format for the dispatch packet. Like I've said multiple times, this is architected. So the first 32-bit field here is the header. It contains things like the format, so if it's invalid or a dispatch packet. Then it contains the workgroup size, the grid size, a pointer to the kernel, and some kernel arguments as well, and then some other things. It also contains a completion signal, so that when the packet is finished executing, that signal is notified so that anybody waiting on the results of that packet can get woken up. All right, let's talk a bit about the barrier packet. So this is used for specifying dependencies between packets. And what it guarantees is that it will not launch any further packets from the queue until these specific signal conditions are met. And what this is used for is for specifying dependencies on packets dispatched from other queues within the system. So I'll just go straight to the format here. So the barrier packet, unlike the dispatch packet, it doesn't have a pointer to any kernels or kernel arguments. Instead, what it does is it has these 5 signals. And the barrier packet won't be executed until these 5 signals have been satisfied. So this allows a programmer to specify dependencies between packets launched from different queues. If you have a packet and you want to wait on executing it until some of these other packets are completed, you would put it in a queue behind a barrier packet like this. So again, like I said before, a user may never assume more than one packet is being executed by an HSA agent at a time. The implications there are that you can't poll on shared memory values. You can't block on a shared memory value unless you guarantee you've ensured the proper ordering and that whatever is going to set that shared memory value has already executed. So you need to use these dependency mechanisms to ensure that, like the barrier bit and the barrier packet. So to ensure all previous packets from a queue have been completed, you use the barrier bit. To set dependencies across multiple packets issued from multiple queues, you use the barrier packet. Okay, so the packet execution. There's the launch phase. The packet execution is split up into 3 different phases. There's the launch phase is the first phase. This is initiated when the launch conditions are met. So this means all preceding packets have completed their launch phase. And this is also where you inspect that barrier bit in order to kind of hold off execution of the packet. So the launch phase is where you're kind of getting everything set up. Then there's the active phase, and this is when the packet is actually executing. So the active phase, you could have multiple packets from the same queue in the active phase in parallel. The completion phase, that's the final phase of processing a packet. And the first step when you're done with processing a packet is you do a memory release fence. This makes sure that all of the data that was produced by that packet is going to be visible to the rest of the system, the consumers. And then it signals a completion signal. So that's done in the completion phase. Here's a simple example over time of what this might look like. So we have 3 packets, packet 1, packet 2, packet 3. And in this case, packet 3 depends on packet 1 and packet 2. So it's going to consume some of the results from those previous packets. So packet 1 is launched, and then it enters the execute phase. Packet 2 can't enter the launch phase until packet 1 exits the launch phase. So here, packet 2 is in the launch phase. And then at some point, they're both in the execute phase here. Now, packet 3 is in the launch phase, but it has this barrier bit set basically saying that this can't be executed until these previous 2 packets are complete. So we know that they're both complete at this point in time here, and that's when packet 3 can then enter the execution phase. Pretty straightforward. Okay, so let's put it all together to kind of with a very simple example. This is an FFT butterfly that most of you are probably familiar with. So these are locations in memory. Here I have a simple 8-entry array. And what these nodes mean is that, for example, this node is computed using this data and this data. Similarly, this node here is computed using this node and this node. So how would you parallelize this and execute this on an HSA system? Well, you can think, let's say you want to split things up into 6 different packets. So you could say that the first packet might read these 4 values. It will produce these 4 values, and it will do that by reading these values and reading these values as well. So that's the first packet. The second packet might be in charge of producing these 4 values, and it does that by reading the entire array as well, so just like packet 1. Then you might say, okay, well, the next phase of computation, I'll have a packet execute and produce these results. And similarly, packet 4 will produce these results here. And you could see where this is going. Packet 5 and 6, they're kind of doing the same thing. So how would you then implement this on an HSA system? Well, you'd have to be sure that because packet 3 and packet 4, they're consuming results from packet 1 and 2, you need some sort of barrier here. Additionally, packets 5 and packet 6 are consuming results from packet 3 and packet 4, so you need a barrier here. So if you look at what kind of the pseudocode would look like, now this isn't, don't get too bogged down into the actual words here, so this is just kind of made up pseudocode. But you would have some queue, and then let's say you have these 2 packets, you dispatch the first 2 packets, and if the system wants, those packets can now be executing in parallel, although it's not guaranteed. Then the third packet is sent with a barrier bit set, and that means that this third packet won't execute until these 2 previous packets have completed. You chase the packet 3 with packet 4, and it doesn't need a barrier bit. Packet 5, it does need a barrier bit in packet 6, because it depends on the results from 3 and 4, and packet 6 then goes behind packet 5. So if your system can support executing 2 packets in parallel, it would do 1 and 2 in parallel, then wait until they're done, then do 3 and 4 in parallel, wait until they're done, then do 5 and 6 in parallel. And then here I put a final packet in to maybe do something like notify me when I'm done. So that's kind of the end result. And so what you see here is that there's no going into the kernel. There's no manually flushing caches in order to get data back and forth. There's no manually copying of data from the CPU to the GPU. It just looks like normal C code. And this is all enabled by the cache coherency, the shared virtual memory, the signaling, and then this architected user mode queuing. And I think I have time for questions. I'm actually about 5 minutes early. So that's it. Any questions?
Hi, my name is Aditya. I work at Intel. So for the user mode queuing, if an app has to directly dispatch something to a hardware unit, then it has to be aware of the hardware capabilities, right? So what does it say about the portability of that app, or does it introduce any additional complexities when creating the app itself?
That's a good question. Maybe, Phil, you could speak to this a little bit better. So
They'll bring this one up.
Okay, all right, good.
Can you bring up mic 3, please? Number 3, thanks. So the answer to this is if the platform is HSA compliant, it can execute the packets that are put into the queue by an application that's written to HSA. One of the areas of the system architecture spec that we didn't get into today is discovery. So an application or a library will be able to discover if there's HSA compliant platform under it, and if so, go down this extremely efficient path and queue directly in user mode. If it doesn't find it, it's going to have a fallback anyway, at least for the next few years. But what Ian was getting at each time he said architected, he means guaranteed compatibility across hardware vendors. So that's really what's going on here. And perhaps it seems a little far-fetched for applications to be putting hardware consumable packets directly in a queue, but as I mentioned, the vast majority of cases, this is going to be done by a library. And library calls like bulk calls or an imaging library, a financial modeling library, a library for oil and gas will be optimized to generate these packets. They are compatible. Okay? Thank you. Stay out. David?
Right.
So one of the things I didn't see mentioned is sort of communication to enable power management at the platform level across an HSA platform. It seems like sort of a natural mechanism to do that might be through this signaling that you discussed. So I guess what I was sort of curious about is how you see that evolving in the future, or is this something that has been developed but is not being discussed right now?
Did you want to take that one?
I don't know if I know the answer to that one. I don't know if I know the answer.
Okay, I'll take it. In the majority of SoCs now, there's already fairly advanced power management, right? So as engines get used, their voltage and clocks are raised. As engines go idle, the clocks go down, or we gate them off. So you already have this concept in SoCs of power management, and different implementations, either do this manually under microcode control or under software control, or perhaps even sort of automatically within the hardware. What we did with HSA through the signaling that Ian described is provide an architected mechanism all the way up to the application to enable the different workloads to flow between the processing nodes in a way where it's very easy for the hardware implementers to do it in a power efficient way. So the fact that the architecture doesn't require polling It has a doorbell. The doorbell is actually abstracted so that different hardware implementations will implement it in the appropriate ways for their platform. Means that the architecture will scale extremely well with power. And as you can probably imagine, the power mechanics on a smartphone are very different than the power mechanics we'll use when we're building out 10,000 node supercomputers based on APUs. But the fact that there is a doorbell so that nobody has to keep polling to know work is there, there's a signaling method right there to enable the different hardware modules to wake up.
You don't sort of see it as a mechanism to allow maybe applications to, say, provide hints to a PMU?
I find it's very rarely a good idea to rely on application hints. Applications get hints wrong. What we want to do is architect the dependencies, so a properly formed application has to signal, and then let the hardware do the right thing underneath it. Thank you.
Yeah, just to speak a little bit more to that, there's nothing to prevent There's nothing to prevent the implementation of the HSA runtime that knows about the underlying PMU from doing clever things, but we don't want that kind of bubbling up all the way past the runtime.
Next question.
Hi, I'm Manoj from Intel.
Yep.
This regards the use of barriers to synchronize within a particular HSA context. The way I see it, the barrier is probably the only mechanism to synchronize across packets that encapsulate tasks that also have dependencies between each other. Barriers seem to be an all or nothing kind of an implementation, right? So if I had a workload that I built with multiple packets, of which I needed to depend only on a subset of those packets, and for others to continue getting dispatched so that I get maximum throughput, what do I do? Am I limited by one queue per HSA hardware agent, or can I build a separate queue on which I can totally block while submitting independent packets onto another queue?
The answer is you can have multiple queues. So if you had some queues that you wanted to, or some packets you wanted another packet to wait on, you could send those in a queue, but then you could have additional queues to send other packets through that had nothing to do with the dependency structure.
So this would mean when I write my program, there is an initialization phase to my program where I set up all these different queues. Can I dynamically create and destroy queues?
That's right. Creation and destruction of the queues is done through calls into the HSA runtime.
Thank you.
Hi, John Mont from NVIDIA. I guess following up on his question, even though I didn't intend to when I stepped up. So you did touch on creation, destruction, and the runtime and all that. You didn't go very deeply into that. One thing I was wondering is the recipient, I guess maybe the agent that's listening to a queue, is that always something coarse-grained like a full engine, a GPU or a DSP, or can that be some smaller grain entity like a work group or something, or even all the way down to a work item?
I don't think there's anything to preclude a specific work group, for example, from having its own queue. It's just really one of an implementation aspect, I think, at that point. There's nothing architecturally to prevent you from doing that.
Yeah, the concept of the queue as designed is envisioned to be attached to something that can be thought of as an engine, as opposed to a subset of an engine. Ian's correct, we don't preclude it, but the way I expect it to work is you'll have a queue for GPU, one or more queues for GPU compute, one or more queues for graphics, one or more queues for DSP, for DMA, maybe a crypto engine, maybe some of the codecs. But yeah, think of it in terms of an engine, something that's going to fetch commands, fetch data, write out data, signal that it's complete. You can slice an engine and have queues that would effectively only provide work to a subset of an engine. It's down to an implementation choice there and how finally you want to divide the machine. I think the more important thing is that for each engine that we consider an entity, there are now multiple queues. One queue per application is an enormous advance on where we are today, but even within an application, within a process space, you can have multiple queues. So that really gives the choice to the programmer or the application designer whether they want to have perhaps a single queue with multiple producers, so you've got multiple threads can put work into that single queue, or if they prefer to use single producer, single consumer semantics, then they allocate a queue per thread. So there's broad choice here, but on an architected foundation. Okay. On this side?
Sorry, Karin. CC with ZTE. So this is great architecture to share data and share the coherency. So I'm wondering, what thing I should take away to leverage is, for data center, I need to load balance. So besides of shared data, I also sometimes need to migrate the chunk of tasks hold to from CPU to other DSP or GPU or other things. So besides of sharing data, what other things I can leverage from your architecture to migrate tasks or even swapping, do hot swapping? Thank you.
Do you want me to take that? Yeah. Okay. So first of all, if we're talking about, so I'm assuming this is a question within a data center. Yes. So you might have a lot of nodes. You know, you might have 50, you might have 10,000 nodes, and you want your algorithm to scale across that machine. So the way I think about this is HSA defines the architecture for a node. And you could think of a node as perhaps a blade in the data center. That might be one socket, it might be two sockets, but within that node, we're coherent. And you don't have to move data back and forth between the CPU and the GPU or the CPU and other processors. But to scale out, we're going to do that non-coherently using message passing and other well-proven techniques that are already in the data center. So, you would expect to, perhaps spread a workload with Hadoop, do some processing on nodes, and then spread or redistribute results for the next stage. Does that make sense?
Thank you.
Hello, this is Sarah Biabani. I'm a system performance architect. And so I'm looking at this from a perspective of an operating system implementer.
Yes.
So there's two things I need to provide for you for the HSA runtime. I need to have some kind of, the shared memory carved out for you. And the other thing that you depend on from me is the signaling infrastructure, right? You're using that. So one observation I'd like to make is that the maximum number of agents working concurrently in flight at any given point in time are basically limited by my signaling infrastructure. So if I can give you a signal, a unique signal, then you can't spawn off a new agent to do your work. Is that a fair assessment?
I think I understand the constraint you're getting at. I mean, I want to address 2 points there. I mean, you said carve out an area of shared virtual memory. I think of it the other way. I think of the shared virtual memory is going to be the whole memory. So hopefully we can have that discussion and see where it goes. In terms of the signaling, are you getting at the need to be able to distinguish a large number of nodes from each other in terms of routing and understanding the delivery of those signals?
Well, in an operating system, let's look at Linux, right? I mean, so there's already a signaling infrastructure. So yes. In order for you to do your DQ and then report that you're done doing the work group work, or whatever level you're working at, so that you need a unique signal to do that, or have some kind of build upon the signaling infrastructure. And in my experience, a lot of operating systems don't have that much unique space, if you will, for signaling. So you need to perhaps build upon that.
So I think there's two answers there. I mean, first of all, we can use any memory location for a signaling object and then conform to an operating system's wrappers on that signaling object. But basically, we don't require special memory or a special handle. We're dealing with platform atomics to do the actual signaling. The other one that may come in from virtualization is the pass ID. So, the number of IDs we can have to represent unique virtual machines or unique processes within a virtual machine. And the pass ID field goes up to 32,000. So I think we have scalability.
I think you might want to clarify that if you say signaling, then that's a fixed signaling infrastructure that you get. But if you start talking about having your own signaling infrastructure, then that's different. So.
Correct, and I think the signaling mechanics we've defined can also support your operating system signals, but we should have that conversation. Thank you. I think this will be the last question, and we'll get to lunch.
Okay. So this is related to the architecture of the dispatch packet. So as it is defined today, is it generic enough to support any kind of accelerator, or is it specific to GPUs for now and can be extended in future?
The intent is for it not to be GPU specific. So I think the fact that we have shared memory, then once you have that, just having a pointer to a kernel and then some arguments for that kernel is often all you need.
So I would like to expand on that a little bit. It's not specific to GPUs, but it is specific to compute. Right? So for instance, this packet could be used very easily with digital signal processors. It could actually be used very easily with DMA. It's not immediately applicable to graphics, for instance. Graphics would need a more complex packet specification, and that's beyond the scope of what we're doing here.
Is it a fixed size, like
yes, it is.
16 bytes or something, and that's intended to cover all the different kinds of accelerators you might have to support in future?
It's 64 bytes, and the intent is to make it compatible for multiple accelerators.
And the basic decision was, if we make it a fixed length, we make the implementation much simpler, and then we looked for the right balance of embedding data and then using pointers to be able to get the expandability without having everything go through pointers, which would be a penalty on performance. So yeah, it's a fixed length packet, and yeah, we believe it's comprehensive for compute.
Great.
All right, I think that's it for the tutorial session. I would have to say this is probably the best presentation of HSA technical material I've seen around. So let's give the presenters a hand, and let's get back here by 2. So we want to be fair to the next tutorial.